Okay, for people joining us, this is a working session where we are talking about things related to our physics project. And in particular, we're trying to understand today things about the relationship between category theory, computational irreducibility, physics, mathematics, and so on. So I want to start with these are some notes Jonathan and I made yesterday. I want to start with making sure that I understand some things. Okay. So let's review a moment. Let's review. Let's just do a little bit of a review of category theory for a minute. Okay. So in standard category theory, the idea is that we have these objects in a category connected by morphisms. So, for example, those objects could be as simple as just integers connected by a morphism, which is a successor. Is that true?
Sure.
Okay.
Well, in that case, the successor function would be a metamorphism.
Why? Because it's the same in every. I mean, normally.
Well,
go ahead.
Well, because a morphism is an arrow connecting two objects. The successor function is a rule for generating arrows.
No, I understand. Okay, so let's try to understand. The successor
function is not a morphism; it's a metamorphism.
Right. So each one of these. So I mean, the morphisms are those mappings from element. In this case, when I'm writing it like this, they're element to element. So it could be, and we could have a generator of morphisms. Right. But now, I'm trying to understand the analogy. Let's say that the objects here were steps in the evolution of a cellular automaton. Okay. Right. And the morphisms are the transformation from one of those steps in cellular automaton evolution to the next one. Right? What is the name of the thing you're describing as a metamorphism in category theory? I mean, what is that concept? Or does that concept not exist? Because normally in category theory, these objects are big named things that all have their own sort of inner life and aren't things that you would just have a large bucket of.
Right. So my internet connection is breaking up a little bit. I'm just going to reconnect to a different Wi-Fi hotspot. I'll be right back.
Okay. Anybody else want to respond to this?
Well, so in typical category theory, the arrows are given and the nodes are given, but there is anything else that is giving some rule or structure about how the arrow should be. That is something beyond the standard category. So in that sense, within the typical definition, you do not have a metamorphism included. It's an additional thing.
Right, but in standard category theory, there's also the transitive closure of these things, right?
That's right. So if you want to represent this thing graphically as a standard category, you can take a graph, take its transitive closure, and make sure that the arrows are bidirectional, and then you get a graphical depiction of a category. And this was also what Jonathan had shown in his bulletin some months ago.
Right.
Sorry, but I missed the question because of my internet.
So we were just trying to point out to your to the graph that you showed in your bulletin of a diagrammatic representation of a category, where you take a graph, take its transitive closure, and make sure that the arrows are bidirectional.
Right. I mean, okay, yeah. So the basic point is, you have this underlying structure, which is a quiver, which is just another word for a directed graph, and then a category is a particular example of a quiver in which the arrows compose associatively, and in which you have left and right.
So wait a minute. I've heard of quivers. Okay, so a quiver is like directed graph between objects, basically.
Right. It's a cutesy name because it's just a collection of arrows.
Oh.
Yeah, I mean, more precisely, the arrows are sort of functions with as source functions and tail functions, and given a bunch of nodes, and using these functions, you can build the arrows by taking a source or a tail function.
Okay, so in other words, the quiver itself is just the collection of arrows, the collection of pre-morphisms, so to speak.
Right. Well, yeah. I mean, they're still morphisms. It's just that they don't yet satisfy the axioms of a category.
Okay. So but to make it a category here. So I mean, this would be, if I were to do this without the transitive closure, that would be a maybe even without the undirected graph here, that would be one of your quiver things.
Right. And so the reason you're taking the transitive closure is because you, in the category case, it has to be okay, basically the way you get from a category from a quiver to a category is you have some rule that says, for a pair of morphisms, how do I compose them? Right.
For a pair of morphisms, you compose them by either you can just go, wait a second. So that's the thing that gives you that composed morphism. That is the jump of two steps.
Yeah. So the point is that the quiver, a category is the quiver equipped with this additional binary operation that is the composition of the sequential composition of morphisms.
Okay.
And the only constraints are that composition should be associative, and it should satisfy left and right, the left and right unit, identity laws.
Well, okay. So a category, in addition, has a composition rule for the morphisms. Fine. Okay. So now let's talk about this in the context of computational irreducibility, right? Because let's imagine that composition there's computational effort involved in each of these morphisms. I mean, I have a feeling that usually in these morphisms, you're just saying there's some space and it maps to some other space, and it just is. That mapping just exists somehow. You're not imagining. It's like functions before Turing machines, so to speak. That makes sense. I mean, like instead of just, a Turing machine tries to give some mechanism to a function, as opposed to just saying a function exists, f of x. Is that a correct analogy?
Yeah, I think that's what we were discussing.
Okay, so but I'm just trying to slowly go through this, okay, to make sure I understand and that we can. Okay, so what we're saying is the morphisms have, there's a computational category theory, so to speak, that in which one is saying morphisms have a computational cost. And then the question is the, what is the cost of the composed morphism? Right? So in particular, if and is the composed morphism just sort of additive on the computational cost of each individual morphism? Or is it something different? So maybe we could do an example here where, I mean, clearly, what's a good example here? Let's say that these things are, I mean, I'm imagining sort of a blockchain-like creature where there's lots of effort involved in each of these morphisms. Is this making any sense?
Well, yeah, again, isn't this just what we discussed yesterday?
Yeah, I'm just going over it again. I'm just trying to be careful and trying to define it better. Okay, so yes,
but it's reasonably well defined, right? It's just, as I say, it's a failure of compositionality. I don't think.
Yes, I know, but let's try and be more precise. Let's try and actually imagine these are Turing machines. Okay.
Yeah. Right.
And let's or cellular automata, and let's try to be precise about what this actually means.
Yes, exactly. And so, as I pointed out in my email yesterday, there are several considerations you have to make. For one, you have to include a notion of partiality, which we haven't yet discussed.
What does that even mean? What does that mean?
So if you have in the most simple-minded sense, you could think of, every morphism is some function.
Yes.
Acting on certain objects, but all of those morphisms are total. Now, you also want to be able to represent computations.
Did you say this in your email? Then I didn't read that piece of email. I'm sorry. Okay. Well, anyway, go on. Yes. All right. So we're talking partial functions as opposed to total functions.
So one needs a notion of partial morphisms, which does exist in category theory. That's the whole idea behind partial combinatory algebras in category theoretic formulations of combinators and untyped lambda calculus. There's a notion of partial versus total morphism. So you can get around that.
Hold on, but I'm not even sure I understand that properly. So let's make sure that. So this is the notion of morphisms to represent partial functions. Okay, so now what does that mean? That means a partial function is a function where there is, quotes, no defined value for certain inputs. But that often means in the Turing machine case, the thing doesn't halt.
Right.
So, I mean, for example, in our language, I can just say, f of 2 is something or other, but I don't define f of 1. That's not because it fails to halt. That's just because it isn't defined. Right? I mean, a partial function could be partial because it simply isn't defined or because it doesn't halt. Isn't that correct?
Right. But those are equivalent ideas.
Are they? I mean, it's not completely obvious to me that those will work the same way, but okay, let's take those as equivalent.
Well, in the standard way you think about computability theory, it doesn't make a difference whether it's a non-halting input or whether it's an undefined input. They're both represented by partial functions.
I know that. I'm not sure that's right. I mean, I understand that's what's done. Okay, I'm not certain that that's the right model. I mean, I think that because the reason I'm saying that. Go ahead.
Well, obviously, in the multi-way formalism, it's one of the nice features of it is that we have higher levels of granularity than that. I mean, this is again, I think, a disagreement that we had back when we were discussing metamathematics, where when we were talking about interpretation of say the first incompleteness theorem and things like that, I was saying a way you can think about that is just that they are elements of the partial order that are not totally ordered. Right, so that there isn't a sort of finite. There isn't a way you can definitively say this element precedes this one.
What are the elements here?
Well, okay, so in the simplest case, they could be sides of an implication. So you have element A, element B. The order relation is implication. But if A and B form an antichain, then it isn't the case that either A implies B or B implies A.
Right.
So that you say that one is independent of the other. And the point is that's a different statement. In the multi-way context, that's a different statement from saying that there's an infinite length path. Which is another, if there's an infinite length path, then they are ordered. It's just that you can't witness the order with any finite amount of computation.
Yes. And
that's a different idea.
Right, I agree. So that's a good point. Okay, so sort of this is the kind of, Gödel's, incompleteness theorem analog.
Yeah, I mean, okay, let me put that in a much less complicated way. If you have a digraph, there's a difference between the digraph being disconnected and the digraph having length paths.
Exactly. Well, I mean, and okay, so let's be specific. Let's make a partial order, right? In which, okay, so case 1, there is no connection, i.e. an antichain. I mean, that would be a one cause of being an antichain.
Right.
Making it an antichain, making the thing, there's no connection between two nodes. And let's assume in this case that our nodes represent theorems. Okay, so in other words, this is the case, I know we need names for these things. Case where nodes are, assume nodes are theorems.
I think, I mean, okay, until we come up with proper names, I think thinking of them as implication order and equality order is not a bad.
It's not bad. It's not bad. Assume nodes are theorems and evolution edges are implications, are implication edges, are implications. The alternative is nodes are expressions, evolution edges are equality. Is it equality? I'm not sure it's equality. It's one-way equality.
Well, you can have either.
What's that?
You can have either.
Yeah, or equality or one-way equality.
Right.
And this is, that second one is more the algebraic story, and the first one, but aren't these just related? Okay, I'm now very, very confused, because in some category theoretic sense, isn't one of these a one category? Isn't this just the two category of which this is a one category?
It would be that way if the notions of one-way equality and implication were somehow the same. But in logic, one makes a distinction between implication, which is the algebraic idea, and entailment, which is the proof theoretic idea. And even though they're sometimes represented with the same symbols, they do actually mean different things.
Okay, let me understand that, because I think this is a good solid confusion. Okay,
right.
So by entailment, okay, so let's talk entailment. Entailment, like substitution. If you just do substitutions and things like that, you have entailment.
Right, exactly. So the point is, implication is an algebraic operation. It's a binary operator that satisfies, that's equivalent to, that where A implies B is equivalent to not A or B. Right. That's just a pure Boolean algebra.
Well, it has actual axioms, whereas you say entailment is sort of pre-axiomatic.
Well, entailment is, if you consider the set of all well-formed formulas partially ordered by the substitution rules, that partial order is the entailment operator.
Right, but it's pre-axiomatic, needs only substitution. It doesn't need any of the axiomatic facts of equality and so on.
Right.
So yes. It's purely structural.
You can have, yes. Exactly. So you can have entailment in arbitrary algebraic theories, even ones that aren't compatible with Boolean algebra, which is not the case with implication.
Well, let me understand this a little bit more precisely. So in Wolfram language, for example, our pattern matching is essentially an entailment story.
Right, exactly. And because of that, the operations between lemmas in find equational proof is entailment, because it's a syntactical procedure.
Hold on. So you're saying in find equational proof, to go from one lemma to another is, I see. Okay, fine. Yes, it's purely structural. And in fact, the way that, the critical pair lemmas are the place where you're using more structure than pure substitution.
Exactly, yes.
And that's the only place where you're using more than pure substitution, correct?
For equational logic, that's true, yeah.
Right. So the point to make here, for find equational proof, the lemma construction is purely structural. So that is, for example, that is the analog of my find replace path business. Find replace path is a lemma construction story.
Right.
Whereas critical pair lemmas. Okay, so what exactly does critical pair lemmas require? It requires this extensionality idea, yes?
Yes, yeah, although but it's not a very strong extensionality principle.
What does it explicitly require? It requires that which has a common ancestor can be considered the same.
Well, basically, what critical pair lemmas are doing are providing one axiom for the entailment operation. It's saying if A entails B and A entails C, then B and C are equal.
Okay, right. That which has a common ancestor. Well, okay. So A. What's a good symbol for entails? Isn't it one of those tail? What is a good symbol for entails?
People sometimes use the turnstile, but that could get confusing.
I want a nice symbol. Don't they have one of these taily things with an entailment with a tail?
I'm pretty sure the turnstile is the standard.
All right, let me see what that looks like. So which one are you saying here?
Can I see it?
The arrow collection. Why is this not?
Oh yeah. Bottom right. Bottom right.
That one there.
Yeah.
Yeah. Well, and that's why at the beginning of a proof thing, it's like assume this. It's like start with that at the beginning, right?
Right, exactly. So when you're writing proofs in the Hilbert deductive framework, you start with that because you're saying basically, this is these statements are entailed by nothing. They're the ones you start with, and then everything else is entailed by those.
Right. It's like the Big Bang.
Right.
I mean, in a sense, we have that same issue. We have a concept of states which are entailed by nothing, so to speak. Which
those are our null goes to whatever events in
right, right, which begin the whole process. Okay, so the critical pair lemma says, if that and right, entails C, then A entails, no, sorry, then B entails, no, wait a minute. Then if A entails B and A entails C,
then B and C are equal.
Right, which means that there's what the heck does that mean? What is that equality notion?
They entail each other.
I.e., B entails C and C entails B.
Yes.
So isn't that statement of equality, is that an obvious self-evident statement of equality? In other words, the two-way entailment, is that the necessary, or can equality be thought of as something? I mean, the notion of equality having a structural consequence, as opposed to just being a pure piece of kind of axiomatic fluff, is not, the connection between equality and something structural is not self-evident.
Well, that's why you need extensionality.
Explain.
So the notion that, because basically what you're pointing out there is that you are implicitly assuming this idea that equality implies that I can reduce the two sides of the equality to a normal form, and then there's some syntactical renaming I can do that makes the two sides equal, syntactically equal.
Right.
And that's not, you're right, that's not self-evident. That requires a statement of propositional extensionality.
Well, it may or may not follow, may or may not be the case. Given this critical pair lemma, may or may not be the case that there's a common normal form. Right? Left to its own devices, there's no reason to think there's a common normal form. I mean, that's essentially, causal invariance. That there is a common normal form, that this implies the existence of a common normal form is causal invariance. And how does that relate to extensionality?
Okay, so I don't. You lost me as soon as you started talking about causal invariance. I mean, this is something that's pre that, right? This is enforcing causal invariance.
I understand that. But if your system naturally had causal invariance, then it would be the case that if this is true, if A entails B and A entails C, then B and C have some common future.
Yeah.
Right, which is not true in general.
Right. That's what confluence is. Yeah.
Indeed. So what I'm asking is the extensionality axiom.
Yeah.
What is the relationship between, and we've talked about this about 75 times, but I'm still, trying to develop the most perfect understanding, so to speak. What is the relationship between an extensionality axiom? Okay, so what will be the extensionality axiom here?
Well, it's exactly propositional extensionality, which in the symbolic case is what I just said. It's that if A equals B, then we can reduce A and B to a normal form, such that the two normal forms can be the variable, the free variables in the two normal forms can be relabeled so as to make the normal forms syntactically equal.
Okay, so you're saying if A equals B, then there is a reduction R of A equals R of B. Well, RA, something or other, where this is a syntactic equality, essentially right. Triple equals.
Yes, yeah, exactly. But it's actually the implication should be the other way around. It's defining equality.
Well, then what's the extensionality statement? What's the axiom?
No, that is the axiom. It's just you've got the implications, and you've got the implication the wrong way around.
So what is the correct thing here? If there is a reduction,
yeah, then A equals B.
Oh, I see. But that's almost a definition of equality.
Well, that's what extensionality means, right? Extensionality is defining the equality predicate.
Okay, but then this. Okay, then what's the relationship to the critical pair business?
Right.
Saying, go ahead.
So the relationship to the critical pair business is you could have situations where there isn't. Okay, you could have equalities that are not decidable if you don't have a confluence system, right?
Wait a minute. You can have equalities, right. Okay, so in other words, so if there isn't confluence, then two things could be equal according to a critical pair lemma. But not reducible to the same normal form.
Right. So the point is that so if you didn't have the ability to, okay, I'm going to call this thing the critical pair axiom, right? The statement you made above about A entails B and A entails C, then B and C entail each other. If that axiom weren't true, then there would be equalities that would be true if the axiom held that you wouldn't be able to prove, right? In a non-confluent system.
Sorry, we have a question on a live stream asking, is this related to the Yoneda lemma? To which I think the answer is somewhat. Can you say?
Not in any particularly direct sense.
What is that lemma?
It's the categorical generalization of Cayley's theorem. It says that if you have a category that's locally small, then it can always be embedded into the category of functors on that category.
Someone was asking, what happened to symbolic discourse language? Was the project abandoned? Absolutely not. It's just there's only finite time in yes, and there's a certain computational irreducibility to getting all these things done. It is absolutely on the docket, hopefully for 2021. Most definitely on the docket. But we are, yeah, there's some new realizations which potentially allow progress in some other areas, and which actually all have a habit of informing. Yeah, it's so interesting how all these things, how connected all these things are. I mean, yeah. Let's not get sidetracked onto that. Although it's not as unrelated as you might think to what we're discussing here. Okay, but anyway, let's go back to this. So what were you explaining here? So right. You're saying
that axiom that you've essentially stated there, that critical pair axiom, that if A entails B and A entails C, then B and C mutually entail each other, right? So if you didn't have that axiom, then there are equalities you can prove with that axiom that you couldn't prove without it. Is basically in a non-confluent system, right? That's sort of what it means to be non-confluent. Right?
Yes. If you don't add the critical pair,
right? But the point is that
this is a generalized critical pair axiom. You're picking a particular A. This is essentially a definition of equality, isn't it?
No. That was the whole point I was making. So this is slightly extending the standard propositional the standard statement of propositional extensionality with a statement that equality, when considered as an algebraic operator, is transitive. Because if you have transitivity of equality, and if equality implies entailment on either side, the critical pair axiom follows trivially.
If you have equality, and equality implies, so in other words, A equals B implies A entails B and B entails A.
Yes, right. And you have transitivity. So if A equals B and B equals C, then A equals C.
Yes.
Then you immediately have the critical pair axiom. It's the critical pair axiom is a special case of transitivity for a bidirectional entailment definition of equality.
Okay, but the reason that can fail, I mean, okay, so the thing you're distinguishing here is, first question is, do these things have a normal form at all? Do they have a common normal form? And then, I mean, it's a question of, do they have a common past light cone? Do they have a common future light cone? If I'm not mistaken. I mean, why is there not a symmetrical discussion that one can have? That is, this is saying they have a common past light cone. You know, so the physics version would be, things are equal if they have a common past light cone.
Yeah.
That's the critical pair lemma axiom. And then another statement would be, things are equal if they have a common future light cone.
Yeah.
I mean, you think this is obvious?
Well, yeah.
I mean, okay.
And the whole point of introducing transitivity of equality is because the past light cone is inaccessible. The only thing you know is the future light cone.
So
you introduce equality so that it becomes decidable.
Sorry. So what becomes decidable? I'm being very dense here, but what?
If I have two expressions, I can't work out in general what their past light, whether or not their past light cones intersect. I can't determine whether or not they emerge from a common expression.
Right.
The only thing I can do is apply rules in the forward direction.
Yes. I mean, if for many ways that things could be set up, yes, that's the case. Right.
Well, that's what general means.
Fine. Okay. So we have two expressions, okay? X and Y, A and B, whatever. We're applying forward evolution, E of A, and we're applying E of B, and we're asking, do these things have a do they intersect? For E is the evolution.
Right.
Do these intersect? And that's our definition of whether A and B are considered equal. It's not clear whether intersect is the right thing, or do they have a common future, as in they have the same normal form? Those seem to be two different questions to me.
Why? If they intersect with a common state, then if that state has a normal form, it's by definition a common normal form.
No, I understand. But these things neither could have a normal form. That's what the whole partial function business is going to be about. Neither has a normal form, but they have an intersecting, neither, if E is a multi-way evolution, these could be two multi-way graphs, like in the case of combinators, SK combinators, where there exists a common normal form for these two, but they could also, both of them could get lost in different ways and not evolve to normal forms.
I'm well aware. Yeah, you can have weakly normalizing systems.
Right. So do you consider those two things equal if they have intersecting multi-way graphs, but their multi-way graphs do not both evolve to the same normal form?
You can do or you cannot. Right. This is.
I know. So this is what I'm trying to tease this apart, because this is going to be relevant to the claim here about Gödel's theorem in multi-way systems, right? Because I mean, okay. So go ahead.
No, yeah, of course it's going to be relevant. Yes.
Right.
Sorry.
Okay. So let's just be clear on what, because when we actually have examples of this, right? We can actually let's pull up an example just for the sake of having something definite to look at. Let us say, let's see, in my absurdly long description of combinators, which I really need to have a different form here. This web form is just crazy. Okay, let's go down here. Somewhere, we're going to have one of these. My gosh, look at that thumb. The thumb is okay, multi-way systems. Come on, multi-way graphs. Here we go. They're getting warm. Those ones seem to have normal forms. Ah, there we go. So that's an example of one that doesn't have a normal form. Whatever. Okay. Okay, so there we go. So there's its normal form, and there's the ways it gets lost. Make sense? So now the question is, if we've got two different combinator expressions here, and they overlap here, but they get lost. I mean, we don't really have a good characterization of the getting lost states, if that makes sense. But what you're saying is, one possibility is that they both evolve to an ordinary normal form, like something like this, right? Can you, what are the buzzwords for that situation?
Well, strong normalization versus weak normalization. And the whole point is that if you have transitivity of equality, then weak normalization implies strong normalization.
Okay, but that means that this can't happen.
Yes, if you have transitivity of equality.
Okay, so then, okay, let me try to understand that. With transitivity of equality, yeah, it's sort of obvious that that can't happen. With transitivity of equality, any form of normalization.
Yeah, then weak normalization implies strong normalization because all paths from a common expression are in the same equivalence class, including the ones that normalized.
Okay. So, okay. Okay, so wait a minute. So we've assumed, so in nothing that we've talked about here, none of these pieces assume transitivity of equality. Is that true? Or am I confused?
Sorry, none of which pieces?
This is extensionality, axiom.
Yeah, right. No, yeah, that's true. We've assumed nothing algebraic about the equality predicate.
Right, but as soon as we're trying to, okay, so basically what you're saying is, as soon as the equality predicate is thought of as somehow algebraic, we're dealing with total functions and we're dealing with things that have strong normalization.
Right. Okay. I mean, so here's the fundamental point, right? So at the very least, your equality predicate should satisfy the axioms of an equivalence relation. So extensionality. So, and we know there are three such axioms. You have symmetry, reflexivity, transitivity. So with extensionality, you trivially get symmetry and reflexivity.
Okay, let me just write down this. Okay, better satisfy the axioms to be whatever you call equality. Better satisfy the axioms for being an equivalence relation.
Right. I mean, we can quibble about whether or not that's true, but that's our philosophical starting point.
Okay, but equivalence relation axioms. Okay, so those axioms are, it's got to be symmetric, right? Mm-hmm. If A equals B, then B equals A. Yep. Wait a minute, what's reflexivity? Is that reflexivity or is that?
No, that's symmetry. So then reflexivity is that A equals A.
Okay, A equals A is true. So symmetric, i.e. Okay, and what's the third one?
And transitivity. That if A equals B, B equals C, then A equals C. So the point is that in the definition of extensionality that we've given up there, okay, it's clearly reflexive because yes. The reduction, reducing A and reducing A, that will always be syntactically equal. It's clearly symmetric because syntactic equality is symmetric.
Yep.
But it's not clearly transitive.
Right.
That's the problem.
Let me just walk through that for a second.
Okay.
So A equals B means there is a reduction that ends up in the same place. Okay, this is not completely obvious to me. Can we give an example? So we want something where the reductions lead to syntactic equivalence. Right, so if we're asking, can it be the case that there is a syntactic equivalence between the reductions of these?
Right, I mean, anytime you have non-confluence, that's not going to be true, right? Because even if we can reduce A and B to the point where they can be made syntactically equal, and if we can reduce B and C to the point where they can be syntactically equal, the reduction you made to B in the first case might be a different reduction, or you might be on a different path in the multi-way system from the reduction you made in the second case.
Unless they're strongly normalizing. If they're strongly normalizing, then it's just going to work.
No. Strong normalization isn't sufficient to guarantee that. You'd need confluence and strong normalization. Even if it's strongly normalizing, and if it's strongly normalizing and non-confluent.
Yeah, it could have multiple final states, for example.
Exactly, right. So that, and the final state that makes A and B equivalent and the final state that makes B and C equivalent could be such that there isn't a final state that makes A and C equivalent because they're on different branches.
Okay, but confluence, I mean, causal invariance obviously doesn't imply strong normalization, but confluence, as usually set up, does. Is that a true statement?
No.
Okay. I mean, the simplest cases of confluence are things like this.
Yes. Yeah. And the procedure you use for getting confluence, i.e. Knuth-Bendix completion, does force strong normalization when there's weak normalization. But actually, confluence and strong normalization are independent properties.
Okay, so you're saying here, okay, let me walk through this again. You're saying here that confluence okay. Well, let's see, where were we going with this? What were we trying to establish with this?
No, so I was just pointing out that this is the reason why you need the critical pair axiom. The fact that this notion, that the standard notion of propositional extensionality that we've given doesn't entail transitivity of equality. And so because you don't have transitivity of equality, different branches of the multi-way system that emerged from a single state are not treated as being equivalent, even though by any reasonable definition of equality, they ought to be. And that's why you need the critical pair axiom. That's why you need transitivity of equality.
Okay, so hold on a second. So you're saying if I look at different branches here of this multi-way system, some definition of equality might consider this state and this state equal.
Right. Well, I mean, any definition of equality that satisfies the axioms of an equivalence relation would consider them equal. Right, because if each of these arrows is a symmetric equivalence, if each of these edges is a symmetric equivalence, then there's a chain of those equivalences that gets me from one to the other.
If they're symmetric, why do we think they're symmetric? Why are they not one way? Why are the edges in the multi-way graph symmetric? I don't understand, because we're assuming something different when we're talking about them as a partial order.
Yeah. Right.
So explain what you mean by them being symmetric like that.
I mean, that they are symmetric. If the rules are equational, then the evolution arrows will be symmetric.
I know, but this is where I get, again, totally confused, right? Totally confused, because we've got these different interpretations and we keep on flapping back and forth, or I feel like we're flapping back and forth between these definitions.
Right. I mean, you brought up the combinator example, which is not even equational. And even if you made it equational, it's equational in a different sense to the sense that we're discussing, but that wasn't.
Oh, gosh, what a mess. Okay, so hold on a second. If the thing if these are two-way arrows here, then I completely understand this concept that these two things should be equal.
Right.
Okay. But okay, this all came from my statement that these two cases are related by sort of one level of by what do you call it when you go from a one category to a two category? What's that operation called?
That's a good question. I actually don't know. Xerxes? Sort of higher order construction.
So just the functors would be some kind of natural transformation, right?
Yeah, but the functors are just the functors take a whole big one of these and map it to a whole other big one of these, right? The functors are not, there's a functor that goes from this to a whole thing. That it's a single functor. It's not the case that there's a separate thing for each of those morphisms. Or am I confused?
No, I mean that's true. I'm just, yeah, I mean
that's the big point of category theory, is that there's a single functor that can take you from one category to another.
Right. But this question of what happens when I extend from a lower order category to a higher order category. Yes, you can represent it in terms of a natural transformation, but is there a particular, is there a...
I'm sorry, why can you? Because when you make this into a two category, what you're saying is that for every morphism here, you're treating that morphism as an object in the higher order category, right? So you're mapping from morphism to morphism. You're creating a morphism that maps from one morphism to another, yes?
Yeah.
Right, but that's different from the functor case where you're taking every morphism here and mapping it to every morphism in another category.
I know that. What's your point?
I'm just being confused here.
The point is that the category is defined entirely in terms of its morphism. Sorry, can be defined entirely in terms of its functors. Right, the family of functors defined over the category can be essentially defines the category. And so then if you swap those functors for morphisms in a higher category, which is what a natural transformation does.
Okay, I don't know what a natural transformation is. Sorry, explain. What is a natural transformation?
Okay, so it's a morphism of functors. It's how you define what these. Okay, so if you have.
Why is it suspicious? It's whenever something's called a natural transformation, why does that make one suspicious? Go ahead. Never mind.
Right. Okay, so given a category or given a collection of categories, you can construct what's called a functor category. So if you have a bunch of categories and there are functors mapping between them, then I can consider each category to be an object and each functor to be a morphism.
Yes.
This thing called the functor category.
Okay.
And the way and the procedure for constructing that is what's called a natural transformation. So it's a morphism of functors.
Okay. So what? So I see. We're trying to answer the question: what is the operation called that goes from? Because this is kind of like the one category to two category story, of which going from the expressions case to the theorems case, if I'm not mistaken. These are like morphisms between now objects which are expressions. And this is now morphisms between those morphisms, right? Because those equivalences between expressions are the theorems.
Yeah.
Okay, look, the thing that I'm trying to get to here is this idea of, what is, we talked about yesterday this notion of a computationally bounded category theory, basically, where compositionality, where you just can't implement, where you could say, just as you could before Turing machines, take a function, any function, right? And post Turing machines, there's a notion of a computable function, then we can do computational complexity theory, etc. So in this case, what we're saying is there's a limitation to the formation of a category because its composition operation isn't, it's not a computable category, so to speak, or it's not computable within some computational bound because its composition operation kind of tries to go too far. But I'm trying to understand what that actually looks like. In category theory, the failure to form a category, the failure to be able to construct a category, in other words, there's nothing wrong. In principle, we can define that composition operation. It's just in practice, we might not be able to implement it. Now, you were going on and talking about partial functions. And are you saying that there is
I was only saying that because look, there are two levels we can have this conversation at a sort of hand wavy level. Or you were saying you wanted to be precise, and I'm saying
I'm trying to be precise. Yes, and so
right. So in that case, we need to formalize it in terms of restriction category. We need the notion of partiality. We need a Cartesian product operation. There's a lot of additional structure we need in order to make this precise. But otherwise, I have the idea I told you yesterday. I have a precise formulation of it.
Okay, maybe we should go over this again. Okay, but I mean, just to give a roadmap for where we're trying to get to with this. The notion is that we have this sort of computationally bounded categories. I mean, just like you might describe something as being a small category. I don't even know what precise definition of small categories is. I'm sure there is one. I mean, that's a sort of finite-ish category. So similarly, we might imagine that we are computationally small categories. Does that make any sense?
Yeah.
Okay, and then we could say that if you have a computationally small category, let's see, I'm just trying to get the logic right. The claim is that by doing this construction that gets you to the infinity topos infinity category thing, I mean, the meta claim that we're sort of beginning to believe is that the act of going to that infinity category is forcing you into essentially PCE, into computational equivalence. That in other words, you can't get to, there's no way to have enough structure. In other words, it's a connection between, it's saying in order to have enough structure to get a meaningful infinity category, you basically have to have something, it's kind of a bizarre version of something like Gödel's theorem. Because in Gödel's theorem, you're saying as soon as you can embed Peano arithmetic, you know that certain kinds of things are true. You know you have undecidability and so on. So the claim here would be, as soon as you can get as far as having a meaningful infinity category, you know that you have, computation universality, and then that implies computational irreducibility, which then implies certain kinds of ergodicity, which then potentially implies this cohesiveness idea and the growth and decay hypothesis idea. Is that the right logic?
Pretty much, yeah.
Okay. So, because I mean, one part to this is there something in the construction of the infinity category that, like Peano's axioms, sort of forces computation universality? Do we know that? Is there something perhaps in the very axioms of category theory that, just like the Peano axioms, are capable of, you can compile to the Peano axioms from anything, from a Turing machine, basically. Can you compile to the category theory axioms from anything? Because that would be a, go ahead.
Well, obviously, in the bulletin, I have an operationalization of this.
Okay, you see, this is the challenge, Jonathan. I am but a computationally bounded reader.
Right, but the construction isn't particularly complicated. I mean, the idea is, okay, so going back to the rewriting system sort of formulation of a category. Okay,
should we bring up your bulletin here? Is it useful to bring it up to look at it?
It might be. It's but so here's the point, right? So anytime we perform a completion in some abstract rewriting system,
yes,
we are constructing a higher order morphism.
Yes.
Right, because we have two paths which are represented by morphisms, and we're enforcing some kind of relationship between those paths.
Yep.
Because we're forcing them to be equal. So the point is that if you have suppose I have an axiom system for an undecidable mathematical theory,
yes.
Then what it means for it to be undecidable is that the Knuth-Bendix completion procedure doesn't hold.
What do you mean by doesn't hold? Doesn't converge?
No, it doesn't halt.
Oh, halt. Yes, right.
Right.
Yes.
Because if it halted, then it would be decidable. So
well, let's just clarify exactly what that means. The Knuth-Bendix procedure would imply that by doing a sufficient number of completions, you reach a normalizing system.
Yeah. So if your system is confluent and strongly normalizing, then it's trivially decidable, because I can just apply. If I want to determine if an equation is true, I just apply all possible rewrites to one side, all possible rewrites to the other side. Eventually, they'll terminate at some normal form.
Right.
So
now, it could be that the Knuth-Bendix procedure itself doesn't terminate, but there exists some way to make the thing decidable.
Sure. Yeah, right. The implication is not two-way, I agree. But at the very least, if the theory is... Okay, it's the case that if the procedure terminates, then the theory is decidable. Therefore, if the theory is undecidable, the procedure will terminate. Okay, so suppose I have some undecidable theory. For instance, any theory in which I can embed Peano arithmetic. Then, okay, the Knuth-Bendix completion, the unfailing completion procedure won't terminate. I mean, by the way, that's what it means for the procedure to be unfailing. It's that if it does terminate, it's guaranteed to be the case that the system is confluent, strongly normalizing, and decidable. Okay, so if it doesn't terminate, why won't it terminate? Well, at any given point in time, if you have only a finite number of rewrites, there will only be a finite number of possible critical pairs. So you could ask, how can it be the case that it doesn't terminate? Well, what has to happen is that for each critical pair lemma you add, that's adding a new rewrite rule, or a new pair of rewrite rules, and that is then introducing new critical pair lemmas, or new critical pairs, and it's introducing them at a rate that at least matches or exceeds the rate at which you're resolving them.
Right. So you're adding new rules to the system, and they allow you to make new branches in the multi-way system. And you can't put all the tentacles of the octopus in a box. The octopus will keep on, the hydra, in some Goodsteinian sense, will keep on growing, extra heads.
Yes, right. You're not chopping the heads off. You're kind of clapping them together. But for every pair of heads you clap together, two more grow, or at least two more grow.
Right.
Okay. So then the point is, if you then start to think about these things in terms of higher categories, what that's saying is, okay, we start with the original rewrite system. Let's treat that as a one category. I perform the Knuth-Bendix completion procedure on all of the critical pairs that exist in that rewriting system. So I'm basically applying all possible higher order morphisms there.
Yep.
So now I've constructed a two category. And the point is that two category has new critical pairs, which I have to resolve again, and I get a three category and so on. So it's precisely in that case that the completion procedure will build up successively higher order categories, and the terminal object is the infinity quasi category.
But you're saying, if in fact, okay, so let's see if we understand the implication.
But on the other hand, it could be the case that I only build up to a finite number of levels, in which case the Knuth-Bendix completion procedure terminates at some time before.
Yeah, I get it. So your basic claim is that so this is construction of the infinity category. And you're saying a way to do it, Jonathan's way to do it, is by iterated completions. But there is no need for iterated completions if the system is if the system always is strongly normalizing, blah blah blah, terminates basically.
Yeah. I mean, if it can be made, yeah. It's not that the system is terminating; it's that the completion procedure is terminating.
Right. Okay. If the completion procedures, if the iterated completion procedures terminate, generating a quotes finished sort of confluent system, basically.
Right. So in this particular way of formulating it, your question turns into this rather interesting question that is I've been unable to find an answer to in the term rewriting literature, which is, okay, so we know that undecidability of the theory is a sufficient condition for non-termination of the completion procedure, but there will also certainly be decidable theories with non-terminating completion procedures.
Exactly. Right.
And the question is, how do you characterize them? And as far as I can tell, there is no characterization. I don't think
okay, so I'm sure it's undecidable whether. Okay, so let's just understand the implications here. So if my original claim was, okay, so your point is, if you construct the infinity category by iterated completions, if the system itself is terminating, then the iterated completions, if there is an unfailing completion procedure, then if the system is terminating, the procedure will terminate. If the system is decidable, the iterated completion procedure will terminate.
Well,
right?
Unfailing completion doesn't actually mean that.
Okay.
What unfailing completion makes no guarantees about termination. It only says if it does terminate, then the system is guaranteed to be confluent and strongly normalizing.
Okay, so this is not correct.
No, that statement isn't correct.
Okay, so but what is correct is if unfailing completion terminates.
Yes, right.
Then the system is decidable.
Yes.
Okay, but you're saying the thing you don't know is this other way around.
Exactly. Yeah, there are, I mean, yes. It is overwhelmingly probable that there are situations in which the unfailing completion procedure doesn't terminate, but the theory is decidable. Because otherwise, unfailing completion would have some sort of godly...
I think it's impossible. Yeah, it's impossible. I mean, it's undecidable whether something is undecidable. And this would make it decidable whether something was undecidable.
Right. But the question is, understanding how to characterize those decidable theories that trip unfailing completion up.
Yeah, when does unfailing completion fail to terminate even when the system is decidable?
Right.
Right. I mean, it's like any. Go ahead. Yeah.
We have plenty of empirical examples of this, right? Where find equational proof halts, even for things like Euclid's axioms.
What do you mean by halts?
Sorry, it doesn't halt, where it hangs.
Right. Yeah, right. This is when does find equational proof hang? And does it mean anything when it does? And what does it mean when it does?
Right. It means something, but the question is whether it means anything other than,
this algorithm happened to fail.
Exactly. It might just be sort of weird details of the unfailing completion algorithm.
Well, I mean, basically, it's the same story as up here. It might terminate happily here, or it might go off and get lost.
Uh-huh.
Okay, but coming back to this question about sort of as we get, okay, so a construction of the infinity category is by iterated completion.
Right.
And you're saying that iterated completion could simply terminate. I'm just trying to get the thing the right way around, because what I'm claiming. Go ahead.
My statement that is the right way around is that having an undecidable theory is sufficient for having an undecidable underlying theory is a sufficient condition for being able to construct the infinity category.
Right. So the claim is, if the underlying theory is undecidable, universal, let's say, then the infinity category is constructible by iterated completion.
Yeah, I mean, constructible is a strange phrase, given that it's not normally what one means by constructible. But
what do you mean by? I mean,
Well, normally, when constructivists talk about something being constructible, they mean, constructible is a finite number of operations.
Okay.
But no, I mean, it's perfectly
quotes constructible. My smart quotes are getting very dumb by having two of them. Okay. Okay. So this means. Okay. So that's quite interesting. So I mean, then the claim would be that on the way to constructing the infinity category, you basically are forced into computational irreducibility.
Well, with regard to constructing the infinity category, the usual story is that if you're there are two ways you can enforce completions. You can at some stage before going to the infinite level, you can enforce some sort of extensionality, and then you can have a completion, and then you do not get an infinity category. Or you don't go for any of the propositional or equational extensionalities, but you go for the univalence axiom, in which case you allow equalities up to homotopy, and then you get the infinity category, and you get then your completion is related more to the univalence axiom rather than a lower level extensionality. So in some sense, what you're trying to say here is that this infinity category, which should come only when you have some kind of univalence, is related to universality of your underlying theory?
I think so, but I need to understand the univalence claim there.
Well, because so in some sense, when you're imposing a completion, you're asking for two things to have some sense of equality. So when they are equal, you say it's complete. And when you do not define equality via any of the other extensionality arguments, and you simply say that the equality is only defined once you have infinite iterations of these rules, as Jonathan was mentioning, then you're imposing equality at the level of the entire structure. That's what univalence is, in a way.
Okay, let me understand that. So you're saying if I stop at a particular level and I've got my completions sufficiently define equality. I'm a little confused.
Well, I mean, there is no equality as such. Just if you stop anywhere, you have to put some extensionality for something to be equal. If you don't impose an extensionality argument midway, then it's not going to be equal. Then you have to allow.
What do you mean by an extensionality argument?
So when you want to say that two things that are equivalent are equal.
Yes.
That's the extensionality argument. Otherwise, if you don't have that, then one can say, well, they aren't. They don't have to be equal. They are only up to some higher level. The equality has to be defined up to some higher level, and then you have to go and check up to that higher level, and you have to keep checking this infinitely many times.
I'm still confused. Jonathan, can you help unconfuse me, or maybe I'm irreducibly confused here.
Okay, so the point with the univalence axiom, which I think is related to what Xerxes is saying, is that, okay, if you have the infinity category, the point is that the equivalences that you form in the infinity category imply all of the equivalences lower down in the hierarchy up to weak homotopy equivalence. Right?
Yes.
So the point is that once you've constructed the infinity category, you can kind of you can sort of kick away all of the infrastructure you used to get there, and you can just define, everything you care about in your equivalence relation. You can just define in terms of weak homotopy equivalences in the infinity category.
Wait a minute. In the infinity category, which is otherwise known as a Rullian multiway system in our world,
right?
There do not need to be critical pair lemmas. because the Rulio multi-way system has all those connections in it. Right?
Right.
So, I mean, the key fact, okay.
So the point is that in the multi-way context, all extensionality axioms can be thought of as being rules that turn paths to equivalences. Right?
Well, but not necessarily one-way paths that turn, branch pairs to equivalences.
Sure.
Right. Okay.
Sure. So then the univalence axiom then becomes that. So the univalence axiom is stating that function is itself an equivalence. Right.
So which function?
The function that turns paths into equivalences.
Yes, I understand that claim.
Okay. The significance of the Rulio multi-way system is, at least in this particular way of constructing it, that in the Rulio multi-way system, that statement is itself a path in the Rulio multi-way system. The extensionality statement is a path in the Rulio multi-way system. Right?
Okay, hold on. The extensionality statement is that if there are two members of a branch pair, they are considered equal. Right, that's your extensionality statement, correct?
Well, that's part of that's implied by it, yes.
Well, be more precise about what it is then.
It's exactly what I said it was before. That if you have reduction sequences on two halves of the equality, then the normal forms are then equivalent up to renaming of the free and bound variables.
That's a forward light cone story, not a past light cone story.
Yes, right. And the reason it's defined in terms of forward light cones is, as I said, because the forward light cone is the only thing that's accessible when you're doing theorem proving. You don't know the history of that expression. It doesn't exist.
So say this again. What are you saying is okay? So the intersection of forward light cones is what? You're saying that is explain. The fact that intersection of forward light cones is considered to mean equality is the statement of extensionality. Is that what you're saying?
That's propositional extensionality, yes.
Okay, so the claim is to say that forward light cones intersect means equality.
Right.
Is a statement of propositional extensionality.
Right. And so then transitivity of equality, as we discussed, then implies that this is the same as saying that there's intersection of the past light cones.
Right. Okay, so as soon as then if equality is assumed transitive, this must also imply that the past light cones intersect.
Right.
But
if I can traverse each evolution edge in either direction, then that's really just saying that any path is a statement of equality.
Yeah, but why can you traverse? You're just saying if you can traverse every edge in both directions.
Right. Because the point is that we've covered all three possible cases. Right. We've covered the case where the two nodes are related by the partial order, in which case they're equal. Right.
Okay. Well, again, we keep on jumping around. This is what's driving me crazy. Okay. In the expression to expression to expression thing, saying they're related by the partial order is indeed correctly saying this is equal to that.
Yep.
In the theorem case, we're saying this theorem implies this theorem implies this theorem.
Yeah, but we're not discussing that. I mean, we're discussing the case with equality,
which is lower level, and for which we're really talking about the nodes as expressions.
Right, right. In the theorem case, equality becomes an algebraic predicate within the theory. It's no longer proof theoretic.
Yeah, I understand. Okay.
Okay, but then the other case is the case where you have an antichain, where they're not related by the partial order, in which case you can only ascertain equality by looking at intersection of forward or past light cones, which is precisely the case that's covered here. And so, now that we've covered both cases, we can see that equality becomes just a statement of path connectedness.
Yes. Okay. Mm-hmm.
Okay. So we can interpret extensionality as the statement that one can turn paths to equivalences. It's a rule that says any path I can turn it into an equivalence. Okay. And that's the starting point for homotopy type theory, right? The notion that all of our equivalences can really be thought of as just being paths in some topological space.
Right.
So
equivalences are, well, let's see. Equality is associated with the presence of a path. Equality of A and B means there's a path from A to B.
Right.
Okay. Okay, so now explain the comment you were making about homotopy type theory.
Yeah, I mean, so homotopy type, the starting point for homotopy type theory is this idea, right? In a sense that this gives us a way of seeing why homotopy type theory, why that starting point makes sense. Homotopy type theory starts from the idea that all of our type spaces are topological spaces, and all of our statements of equivalence are just paths in those spaces.
In fact, when you think about it in terms of paths, the reason why homotopy comes up is because when there are two paths for going from A to B, then you can start asking about equality between those paths.
Sure.
And that's why the idea of equality as something that is homotopic, as opposed to just at the lowest level.
Right. And the connection to what we're discussing is that those equivalences between proofs in homotopy type theory are like our critical pair lemmas, right? Because they're
Yes.
saying we've got these two paths between these 2 points, but actually we're going to consider them to be the same.
Yes.
Right. Okay. So the place where this gets a little bit funky is when you then look at the infinity category, or in other words, you look at the Rulio multi-way system.
Mm-hmm.
So then the statement of propositional extensionality itself is a path in the Rulio multi-way system, because the Rulio multi-way system by definition contains every possible statement.
Yes.
Which means that all the extensionality principles that you've used to build up to the infinity category, to build up to the Rulio multi-way system, can just be replaced with a single path in the Rulio multi-way system corresponding to that statement. And that is the homotopy. That's the univalence axiom.
What's the univalence? I'm sorry, which part of what you just said is the univalence axiom?
The fact that the extensionality rule can be considered itself to be an equivalence and therefore a path is the statement of univalence. It's like you've used all these different equivalence relations to build up to this this infinity category object, and then univalence is stating you have univalence in the sense that actually ultimately there's only one equivalence relation, and it's
kind of interesting because it's kind of like a compilation story. It's
a lot like bootstrapping in compiler theory, in the sense that you've built up this big technical superstructure to compile the infinity category, but then the infinity category then becomes self-compiling in some sense and can kind of reproduce everything below it.
Right, but it's also not self-evident that you would be able to compile the statement of the univalence axiom into a pure path in the Rulio multiway system. That's not, I mean, that's like, the Gödel's theorem thing, compiling this statement is unprovable into arithmetic is the non-trivial part.
That's the thing. It's actually, so you're not encoding the statement of the univalence axiom can't be encoded as a statement in the Rulio multiway system. The point is that the statement of the general statement of extensionality, that paths turn into equivalences, can be encoded as a path in the Rulio multiway system. And so then the univalence axiom is saying that all I have to do is say that path is equivalent to an equivalence. And then the statement that all of the other paths are equivalent to equivalences follow from that statement.
I see. So it's a definition of equivalence that can then be derived from this one equivalence about this sort of superpath equivalence. Then implies.
Yeah.
I still don't really have my brain wrapped around this properly. I mean, I understand. Oh, gosh. Let's go back to the computational boundedness question. Okay.
Right.
As we get out to the Rulio multiway system, this is going to relate to computational complexity meets Rulio multiway systems, I suspect. Because imagine a computational complexity for, in these categories, right? The claim is you can only go so far in, morphism before you've used up your computation budget, basically. Is that making any sense? That is, from one object to get to another object, even though category theory said, oh, there's just there's this compositionality and there's this jump that allows you to get there trivially, it just isn't true. You can't just substitute in, oh, there's this single unit composition thing. You really have to go through the irreducible number of morphisms, so to speak, to get from one object to another. Am I being confused?
I thought that's what I explained yesterday. Am I misremembering?
Perhaps you're re-explaining the same thing. That's very common.
I thought what I said yesterday was that there's a way of formulating computational irreducibility as a failure of compositionality.
Yes, but I'm trying to explicate that concept, right? So I'm saying there's this,
right? So composition. So the standard categorical picture. If we take a category and we enrich the arrows with a statement of complexity.
Yep.
Right? So each arrow has some unit of computational complexity.
Yes.
The standard compositionality idea is assuming perfect reducibility.
I know. Right. Exactly.
Which is what I explained yesterday.
Right.
So full computational irreducibility is the case where the computational complexities are perfectly additive. And then there's a whole spectrum of intermediate cases. And the question I was asking yesterday is the characterization of the intermediate cases. And I had this conjectural idea about formulating it in terms of these higher categories. And I now have a more concrete way of doing that.
Okay, well, that's interesting. But hold on. So a very simple-minded thing is composition basically doesn't work because composition is a sleight of hand to basically give you something computationally to say it's computationally cheap to jump over many morphisms. Right? I mean, it's like what often happens in mathematics. It's not realizable.
What means?
What's that?
I thought that's what we were. I thought that's what we were using the phrase failure of composition.
Yeah, I know, but I'm trying to dig inside that phrase because I think that phrase is a little bit, what does it actually mean? What does it actually mean when it means?
Like I say, if you have an annotated category, or I mean, if you want to be very, very kind of mechanistic about it, if we have a quiver that's really a weighted graph,
yes,
and we're using that quiver to essentially enrich the category with this additional complexity structure, then failure of compositionality is the statement that category is not closed under the action of composition.
I understand. Or that the weights on the composition, the supermorphisms, are just, in a sense, sums of those other weights, for example.
as I said, the perfect computational irreducibility is the case where the morphisms are added.
Right, okay. So now let's consider the case.
Reducibility is where the morphisms are constant, where the operation makes no difference.
Yeah.
And then there's a spectrum of intermediate cases where it's
okay. Right. So now you think you figured out the intermediate cases.
No, I think I have a structure for thinking about what they are in terms of these categories.
In terms of what?
In terms of restriction categories, which are the way of formulating, partial combinatorial algebras and things.
I do not know what a restriction category is, and maybe that's what you were trying to explain half an hour ago.
Right.
Okay. Right. So you were trying to explain that things to do with partial functions.
Mm-hmm. Right. Okay. So the idea is this is not a new idea. This is this is the standard way you think about combinatory logic, and the way you construct partial combinatory algebras is you construct this thing called a restriction category, which is just an ordinary category, but which has a restriction structure. And what that means is for every morphism, there is another morphism that satisfies certain axioms, and that morphism effectively acts like a partial map operation. So if you think of every category can be thought of as being a category of total maps, but a category with a restriction structure can be thought of as being constructed from a category as being a category of partial maps.
Okay, what is a partial map?
Well, it's like an ordinary map, but where the output is not necessarily defined.
Okay, so we can have an object, and for some variance of that object, the morphism which would normally take it to another object goes off and gets lost.
Right. And so, in fact, I mean, it's an amusing relationship, but the object you get out is exactly an open graph of the kind that we were studying in ZX diagrams and stuff.
What is an open graph?
A graph where edges don't necessarily have two vertices at the endpoint. You can have edges that kind of hang loose. So when you're formulating like quantum circuits, you have open edges because you have inputs and outputs of the circuit.
I have to say that open edge is a better term. I mean, I call these hairs, right? Because they come up in the earlier, trivalent graph formulation of graph rewriting.
Right. Yeah, I mean, they're the things that appear in the inputs of your trivalent graph rules.
Right. Okay. So open edges is a better name than hairs. Should have thought of that one years ago.
Yeah. So anyway, these open graphs. So when you talk about quantum circuits, or you talk about ZX diagrams or any of those things, you're really talking about open graphs rather than ordinary graphs. So then if your quiver is instead a directed open graph where you can have morphisms that kind of start at some point, but then they don't really go anywhere, then you can think of that. Then you can think of the resulting category as being a sort of a category of partial functions, a category of partial maps.
Okay, so wait a minute. So what we're saying is, this is okay. Partial functions are represented by hair, aka open edges, by the presence of these hair edges. So you're saying that it could be something which actually ends somewhere, or it could be just a get lost edge.
Right.
Right?
Right.
Okay, so the thing has and a get lost edge. This is a concrete realization of a get lost edge. It just goes off and loops forever.
Right.
Okay.
Yeah, and I think this is how we got distracted with incompleteness stuff. Is the question of the ordinary computability theory way of thinking about this is that the get lost edges are the same independent of whether the thing is an infinite path or a disconnected sort of multi-way system.
Right.
And the question was, could we somehow produce a more refined version of computability theory that actually made that distinction? I think that's how we got distracted.
Right. I just don't. I think that the very structural syntactic case of disconnection is a much more trivial case than the case of getting lost through infinite paths.
Yes. The point is, disconnection is not something that really, and in these kind of equational systems where you start from a finite collection of axioms, unless you have one axiom that's just like completely independent of, that's like doing its own thing and doesn't have anything to do with the other ones, you will always end up with a connected multi-way system because you started out from some connected initial conditions.
Yes.
The cases in which you get disconnection are extremely pathological ones where you basically sort of force disconnection.
Yes. Okay. So it's mostly, if you can't get from here to there, it's because you got lost on an infinite path.
Right.
Okay. But so now, okay, so the other insight that you had was this thing about foliations and the formation of a foliation procedure that respects the partial order in the multi-way graph being something that, depending on the structure of the multi-way graph, could be an unbounded computational effort.
Right.
And the claim that for that to be a bounded computational effort is something associated with finite dimensional space.
Right, exactly.
So let's walk through that again. So the basic claim is, in the multi-way graph, or in a causal graph for that matter, being able to identify these time slices, what is the input for this? The input is the input a multi-way graph? And then you're asked, give me a foliation procedure for this multi-way graph that...
So the standard way I've been operationalizing it has been thinking about it in terms of gauge choices for an initial value problem. In which case, if the function is one that takes in a branch-like hypersurface and outputs the next branch-like hypersurface.
Right. Okay, so so you're saying, okay, the foliation generator, the foliation function, so to speak. Foliation function, given a space-like or branch-like hypersurface, branch-like in the case of the multi-way graph, give me the next one. That's a pretty big ask to be able to do that.
Right.
So what is the actual operational procedure for doing it? Do you need that in the general relativity, in the numerical relativity stuff you're doing?
Yeah. And that's what the ADM formalism gives you, or the BSSN formalism in the case I'm using.
Okay.
The point is, okay, let's take the causal graph case, because it's generally easier to think about coordinatizations of hypergraphs than branchial graphs. There are really two pieces of information that for any given event, if you want to know the next, the event on the neighboring on the neighboring space-like hypersurface, there are sort of two things you need to know. You need to know the time-like distance, i.e. how many causal edges separate that event from the future event. And you need to know the spatial distance, i.e. What's the average graph distance between the place where this event got applied and the place where the future event is getting applied. Right?
Well, you need to know, yes, you need to know the time-like distance going down a time-like edge.
Yep, and you need to know space-like distance and space-like vector. So you need to have some way of saying, given the position of this event in the hypergraph, where is the position of the next event in the neighboring hypergraph?
Yes, for the next transversal, so to speak, the next slice of the foliation.
Right, and that's exactly what the alpha and beta I parameters give you.
I understand. For the if you have a civilized space, you can define alpha and beta I. But here, instead, we've just been given a graph.
Right.
So it's far from evident. I mean, in the continuum limit, we can understand what that is if there is a continuum limit. But if you're just given a wild graph, knowing the time-like future is just what's in the light cone.
Right.
Knowing this anti-chainery going off in the space-like direction is much less trivial.
Right. And so my discrete differential geometry framework gives one a way to do that if there's a finite dimensional limit.
Explain
Explain how it works? Or
No. Explain that statement. I mean, you're saying.
So given a hypergraph, I have a procedure for setting up a coordinate basis of that on that hypergraph.
Okay. Is this something we already know, or is this something new?
I kind of mentioned the idea before, but I don't think anyone had implemented it until now.
Okay.
But the basic idea is, so we know how to take inner products in a graph, right?
Explain.
So if we have two geodesics, if I have geodesic A, geodesic B, and they both emanate from the same point, then I can produce a projection of geodesic A onto geodesic B by just saying, okay, I'm going to look at, I'm going to take the shortest distance between the end point of geodesic A and all points on geodesic B.
Right.
And I'm going to pick whichever one is the shortest. And that's
that's the projection.
That's effectively dropping a
perpendicular, exactly.
Yeah, from A to B. And then I just look at what fraction along the full geodesic of B that constitutes, and that gives me the inner product.
Mm-hmm.
So then, if the shortest path is from the end point of A to the origin point of A and B, then we treat them as being orthogonal.
Mm-hmm.
Okay. So that means that and I have these dimension estimators that allow me to work out what the limiting dimension is. So then I take the ceiling of that, and then I construct a system of a collection of geodesics that are all mutually orthogonal.
Right. Okay. Fine. I get it.
And then any point can be constructed. You can take a projection of any point onto that coordinate axis, onto that collection of coordinate axes, and that point is then uniquely specified by that projection.
Although I don't quite understand how you make this sort of extended chart, so to speak, where you go from one. I understand from a given point, you know what the geodesics are emanating from, what the orthogonal geodesics emanating from that point are.
Right. Yeah, I mean, how local the coordinate charts or how local the coordinate bases have to be, that's difficult to know. And basically, there's a function in my there's an argument in my function that tells you how local you want those coordinate charts to be. And if they're too non-local, then you can end up with having having underdetermined coordinate systems and horrible things like that.
Well, right. I mean, if these things are, I mean. This is the story of coordinatizing anything. Go ahead. What were you going to say?
I'm kind of curious to run Quinn's, cusped orbifold examples through this to see exactly what happens to the coordinate bases of the cusps. Because what you should see is a forced discontinuity.
Right, but the coordinate bases of nearby, I don't quite understand. I mean, there's a complicated local gauge type story between the coordinate basis of one point. Right, you construct its coordinate basis by your orthogonal geodesic construction. Then you can do the same construction for a neighboring point, and there's absolutely no reason to think there's any correspondence between the orthogonal geodesics for one point and the other.
Right. Okay, so then you have to make. I mean, this is why you need that essentially that cutoff argument I mentioned. So obviously in the continuum case, you're assuming that the space is continuous, and what that means is that I can take a neighborhood. I can treat the
where it's nearby
coordinate basis. So in effect, unlike in the continuum case, we have to specify explicitly what that neighborhood should be. At what point should we impose the cutoff?
Walk me through that again. So we've got two points, and we construct these orthogonal geodesic bases at those 2 points. Now, I'm sorry, what was the cutoff for? You're saying...
The point is, if those 2 points are within a certain distance of each other,
yes,
then the claim is that I if I construct the coordinate basis for one of those points, at one of those points, I can measure the other point relative to that coordinate basis because it's nearby.
Okay.
Because the point is, if you have to construct a coordinate basis for every single point, there's no point in doing it because every point is just going to be the origin.
There's a lot of points running around in this discussion. Yes.
Right.
Okay.
There's no purpose. You don't gain anything from that.
Yes.
It only makes sense if you construct the coordinate basis at a point and you apply it to a collection of points that are within some neighborhood of that point.
No, I agree. And I think this is partly the story of your finite dimensional space thing, that you don't get to do that. Maybe I'm wrong here, but I think this is is the space cohesive or does it fall apart?
Well, that's slightly different from the finite dimensional thing. I think that's more related to the ergodicity thing.
Maybe.
The finite dimensional thing is ensuring that the number of, obviously the number of basis vectors that we need remains bounded. The number of basis geodesics.
Yes.
And that therefore the complexity of specifying a point, and in particular of specifying the shift vector that maps from one point to another, remains bounded.
Okay, that's an interesting argument. Okay, so let's walk through that argument for a second. Okay, your claim is that this is again with respect to, can you construct a foliation function? Is there a computationally bounded foliation function, right? And your statement is, no way, if the number of coordinates in the coordinate basis is infinite.
Right.
That's one of the ways that a computational bounded foliation function can't exist.
Right. So at the very least, imposing computational boundedness of the foliation function enforces limiting finite limiting dimension.
Right. Which is otherwise saying, but that feels like a more informational argument than a computational argument.
Yes, in the sense that it's relating to algorithmic rather than computational complexity. Yeah, that's true.
Right. I mean, you just can't read all the coordinates in finite time.
Right. As you well know, it's possible to convert any algorithmic complexity bound into a trivial computational complexity bound. So they're kind of related, but
yeah, they're kind of related. But I think there's a tighter relation here. I bet there's a tighter relation, because I think you can't end up with an infinite number of hyperedges in finite time either, which is what you need to get an infinite number of, your infinite geodesics thing. In the end,
wait, I don't think that is true.
Okay. I mean, the infinite geodesics, how does that relate to your dimension estimator? In a sense, the fact that there's an infinite number of geodesics is precisely the statement that the ball centered at that point, grows infinitely large.
Right, exactly, and that's currently how that construction is working. I'm assuming, obviously incorrectly, that the space is not a fractal, and that therefore by taking the ceiling function of the Hausdorff dimension estimator, I can obtain the number of linearly independent basis vectors, which obviously isn't the case if it's a fractal.
That's not the case. But I think the thing you've argued recently is that the way to think about these tensors with arbitrary numbers of legs is precisely just by looking explicitly at the geodesics without asking about this orthogonality condition. Because as soon as you have the orthogonality condition, you're forcing, that's integerizing things to ask about orthogonality.
But obviously tensor, the whole reason for using tensors in GR is for covariance, is precisely for not introducing coordinate bases. And so, yeah, I think it's the case that actually this way of thinking about tensor projections just in terms of pure geodesics is a very elegant way of thinking about things, because, something like a hypergraph is fairly naturally a covariant object. But the point is, for foliations, you are having to impose a coordinate basis, and that's where it gets ugly.
Let's walk through that for a second. Your point is the foliation function is producing a one-parameter family of slices, basically.
Right.
And by the nature, by saying, but the thing I just said, one parameter, is basically that in itself implies a coordinatization.
Precisely, yeah. And is therefore somehow against the spirit of general covariance.
Right. Well, it's the fact that time exists forces coordinatization.
Right.
It's like the critters in Arrival didn't have this problem because they didn't have a notion of progression of time. It's just like time is just this sort of always, you get the whole gulp of time together, so to speak, rather than having a progression through time.
Right, just like a photon.
Yeah, he sighs.
No?
Let's think about that for a second.
If a photon had an internal representation of the world, that's presumably what it would be, right? It would get...
Let's think about that for a second. So your claim is the photon that started at the, at recombination, at the last scattering surface in the Big Bang, no time has passed for it. What's that?
Yeah, I mean, if, what it means to be a null world line is exactly that if the photon had a foliation function, it would experience exactly zero time-like distance between the recombination time and future null infinity.
Right. Of course, anytime it has any interaction, I mean, this is what we know from, just walking through this just for a second. The thing that's a little confusing for us is that our photons do have events associated with them. I mean, we believe that photons have, actually, let's just walk through this for a second. I mean, do we think, because what you're implying is there is simply no event between recombination and now, so to speak. If the photon didn't scatter, it literally nothing happened to it. No time passed. No, the photon did no computation between.
Right. So it's not necessarily okay. You could imagine this situation, right? You have some topological obstruction. The obstruction itself is invariant, but there are events that move it around.
Yes.
That still acts like a photon because if it had an internal,
yeah, right. It has no internal notion of time. No
right.
Time has passed for it internally.
Exactly.
Its internal state, its brain is still in the same state as it was at recombination, so to speak.
Precisely, but there can still be events that affect the hypergraph immediately surrounding it in such a way as to propagate it.
Yeah, earlier today in that completely different discussion, this notion of transition radiation when you have a change of dimension is one that I think is interesting to think about. And not unrelated to this.
Right.
If the ambient, so in other words, do you essentially generate more photons? Is there any necessary sense or not in which, as you go from a region with one, given a topological obstruction, if you go from a region with one large-scale effective dimension to a region with a different large-scale effective dimension, what does it mean for the topological obstructions? And my guess is there has to be transition radiation of some kind, because imagine that you have this, imagine that the kind of spherical wave, you've just got, there's more to the spherical wave if you have 3 + epsilon dimensions.
Right. I would have expected that there should, for combinatorial reasons, there should be both transition radiation and absorption.
Well, it depends which way around. I suspect going to lower dimension, there's transition radiation. In other words, lower dimension, as you go to lower dimension, there's an extra sort of piece of photon that has to be there that wasn't there before. And as you go to higher dimension, there is, you lose some photon because it just gets lost in the structure of space.
Right, which would be the transition absorption. But I would have thought that both processes should exist in both directions, although admittedly the balance will be different. Because
possibly so, yeah.
What I would expect is that there should be some sort of quasi-Ramsey theoretic argument that says that for hypergraphs of different limiting dimensions, the families of stable topological obstructions are different. And so then when you transition from one to the other globally, certain topological obstructions will be absorbed into the structure of space and others will be emitted.
I understand the claim. Yeah, right. So I mean, what you're basically saying is what counts as space and what counts as a topological obstruction is different for different dimensions. And that something just becomes, oh, I'm just part of space.
Yeah, that's a nice way to think about it.
Right. And so you don't treat it as a particle. I got to learn more about, in the there's no new idea under the sun category, right? Between Kelvin thinking about atoms as knots in the ether, to Hilbert apparently saying you've got to be able to derive the electron from Maxwell's equations. It's just, these ideas have been around a long time. It's just not, I don't know whether any of these people made much progress on them. I do want to understand what Hilbert figured out about the continuum limit of atom. I mean, he spent 20 years working on what the continuum limit of, discrete atomic type systems is. I don't know whether he got anywhere with it. I know of no publications from him about it.
Hang on, that's I hadn't heard that Hilbert quotation before.
What about the electron must derive from Maxwell's equations? Yeah,
right. Because we should be able to operationalize that.
Well, probably yes. I mean, go ahead.
So because if we use this kind of Graham-esque formulation of gauge invariance, right?
Yes.
Suppose we take let's take some trivial discrete approximation to the circle group, C6 or something. Mm-hmm. Then we can construct the associated fiber bundle for a given base space, and then we can look at if we had a base space with a particular class of topological obstruction. Under what situations would the local coordinate bases that you got out be invariant, be the same as if that topological obstruction weren't there?
Right.
And there should be some purely combinatorial classification of that. That it may even be, one may even be able to derive from first principles.
Right. Well, you're saying that the existence of the particle. I mean, this is the non-trivial part. The existence of a photon is easily derivable from local gauge invariance. The existence of an electron is not easily derivable from local gauge invariance.
Right.
The only thing that is derivable is magnetic monopole type stuff. So yes, I mean, it is non-trivial that Hilbert was thinking about deriving the electron from Maxwell's equations rather than the photon, which is sort of trivially derivable.
Right. But the point is that the magnetic monopole stuff, that's all to do with holonomies in the fiber bundle. Right, it's looking at elementary Wilson loops in the bundle.
Yes,
and similarly, the photon is looking at excitations essentially in the bundle. But the electron would be a consequence of the local gauge invariance, not for the bundle, but for the underlying base space. I think.
I understand. Yes, I understand. I mean, yes, I agree.
And because people normally think about the base space as being some homogeneous model space without obvious topological, without non-trivial topological properties, there's no reason to.
Right, I understand. So you're saying lifting it to local gauge invariance from this base space, from this messy discrete base space, to have that local gauge invariance in the bundle implies certain things about the structure of the base space.
Right, exactly. And so although we've been kind of assuming that the base space is some perfect, grid-like model space, you could also consider a grid-like model space that had an obstruction in it, but an obstruction that just for combinatorial reasons happened not to affect the construction of the fiber bundle.
Right. Well, so what this would be saying is, given the structure of space, the existence of Maxwell's equations, effectively, aka local gauge invariance, in the bundle, would imply the existence of the electron. Yeah, that's an interesting idea.
So is it there already a statement about, so when you want to think of electrons, you normally think of something like a spin bundle. And on your base space, if instead of the usual fiber, if you have a spin bundle, then there is some holonomy argument based on these Stiefel-Whitney classes that ensure the existence of that spin bundle and following that an electron. So isn't this so in that sense the spin bundle, or rather the existence of the spin bundle, puts some conditions on what type of base spaces can have such a particle and not. So it's kind of similar to what Jonathan is saying.
I don't know enough about what is, okay. So explain the difference.
So I'm just making the point that the point that Jonathan just made, that you need looking at holonomies in this fiber tells you something about the type of base spaces that allow such fibers. So I'm just saying that this in the typical construction of describing fermions via some kind of bundle, there is this notion of a spin bundle as opposed to the tangent bundle, and the existence of fermionic particles depends on some holonomy invariance, in this case it's known as the Stiefel-Whitney invariance. I think there are two of them, and you have to check for both of them. So in a sense, when you want to talk about electrons, you are talking about some special type of fiber that has to exist on the base space.
What is the definition of a spin bundle?
So let me see. So with the usual so when you have a fiber on a base, that fiber has some it has some kind of gauge group under which it transforms.
Right.
So the spin bundle is a fiber which transforms under the spin group as opposed to just the orthogonal group of rotation.
Okay, fine. Okay, but that's not, I mean, you could have, fibers. It's pretty common to have fibers that have, SU groups and so on as their internal symmetries. It doesn't have to be an SO group. But this is saying these are the spin groups as the internal symmetry of the fibers.
Yeah, so I'm just relating this point to what Jonathan just said regarding Graham's project. Given that you have some special types of fibers which have very specific transformations, that will ensure the existence of the holonomy properties that one usually identifies with the existence of fermions.
How do fermions come in usually in these? What's the relationship between fermions and the spin bundles? I mean, because normally, in a normal treatment of a gauge theory with fiber bundles, there isn't any discussion of. I mean, the whole fermion story is a different story.
My understanding is that the spin bundle, if you take a local section of a spin bundle, you get a spinner, so you get a fermion field.
Fair enough.
And that equivalently, the spinner bundle can be thought of as being a collection of fermions with a gluing axiom defined on them.
Okay, fine. Whereas the other ones are some kind of tensor, non-spinner creatures. Well, but yeah, okay. We got distracted by Hilbert here.
Right.
William on our live stream is asking, can there be more than one time dimension? The answer is no. Computational irreducibility implies only one time dimension. And we had a great argument for this months ago, which I'm now forgetting. Do you remember how this works, Jonathan? There's a really nice argument for this. That if you have more, go ahead. Sorry. Basically, computation is the progress of time. And yes, there's no sense in which you can have sort of two orthogonal directions that both progress computationally. That's what you need to have more than one dimension of time. That essentially, as soon as you have computation universality, so to speak, all dimensions of time collapse. That two different kind of dimensions of time are both leading you, are both doing computation, but those computations are equivalent. I think that's the argument.
But okay, so if I have a causal graph that starts off connected, but then a single cosmic event horizon forms. So I've now just got two causal graphs that are effectively two causal graphs that have a common past history, but they're now going off and evolving independently.
Go ahead. Then you've got
two independent foliation functions, one for each half.
You're right. So if you can have an observer who spans the two parts of the cosmological event horizon, then you've got the observer has a leg in two different time functions.
Right. The point is that I think computational irreducibility says that you can never have two independent time functions that are observable, by a single observer.
Right, except insofar as could an observer span a cosmological event horizon? That's an interesting question.
That's a sort of alien physics question.
It's an alien physics question. I'm going to write that down as being part of my alien physics. Alien spanning a cosmological event horizon.
Right. Could the alien choose which time function to evolve? That would be interesting. If they had they held two mutually orthogonal time directions in their head, and they could evolve either of them at will.
Right. Well, let's think about that. An alien. I mean, because in a sense, your interpretation of quantum mechanics says we're all aliens in this sense, because we're doing completions across multiple paths of the, multiple branch-like paths.
But the completions are there, in a sense, exactly to prevent this from happening. It's saying that you can't have two time functions, because as soon as you get the beginnings of two time functions, you kind of merge them back into one.
Well, I know, but look, the point of your interpretation of quantum mechanics is that our brains, to make sense of the world, are choosing to consider these different branches of history as the same by virtue of imposing the way we think about it, the way we model what's going on is to have that completion. The mechanism by which we have that completion is that we too are branched.
Right. And so then,
in other words, that completion is merely a model of how our brain is working. It is not a mechanistic story of how our brain is working. It's like saying, you've got Laplace's equation, a boundary value problem of some kind. It is not the case that is a description of how that works, but it is not a sort of mechanistic, time-evolving description of how it works.
Sure. It's really just the statement that an observer should have a kind of a recognizable identity that remains recognizable throughout their dynamic history. And so even though the observer is branching, there has to be the elements of the different branches have to be kind of related by some equivalence class in order for the observer to be recognizable or recognizably identifiable.
Well, yes, but my point is that is a from the outside model. What's that?
I agree, of course. It's not meant to be a complete theory of observation. It's meant to be a partial description of what observation entails.
Well, it's a way of describing what it means to be an observer, is that you maintain that coherence. Right? That is the definition of being an observer. Being an entity, an observing entity, is. This is a different topic here. We're going to add this is a completely different topic, observers.
So if something was to prevent the completions, would you then say that would at least be one necessary condition to allow for more than one time existing?
Yeah, I guess so. But being an observer means you are let's call it an integrated entity.
Right.
Which you have an identity. You have an identity.
Which leads to this rather amusing question of, if you considered the alien who is able to whose consciousness could span two halves of a cosmic event horizon, would they perform space-time completions?
Yes, right.
Considered.
Yeah, okay. Would an alien spanning an event horizon, either any kind of event horizon, right? Cosmological event horizon is easier.
Yes, although Yeah, I mean, it's in the conventional way you formulate completions. Actually, you wouldn't need to perform them for a black hole event horizon, because anything from the outside can get in, and once it's in, it will strongly normalize because of the singularity.
Yeah. Okay. Okay. Well, so the question then is, this is like integrating. This is like you're an insect and you've got all these weird little ommatidia eyes, and you're integrating, or a horse or something with eyes on the sides of its head or whatever, and you're integrating experience from those two eyes. This is the horse alien case. Horses
Right.
do have. Is that the horses? Yes, they do have eyes on the sides of their head, right?
So do rabbits and things. I think pretty much any predated mammal has eyes on the side of their head.
Okay, all right, okay. Rabbit, the rabbit alien. Okay, so it's certainly people in the not very amazing imagination of certain science fiction writers. I'm sure there's somebody who has rabbit aliens. It's rather, I think the rabbit alien is definitely less exotic than the space-time completing alien.
Right.
So an alien who does space-time completions go ahead.
The reason I ask this is that the question is how is a space-time completion different? Is it different from our natural construction of simultaneity surfaces?
Yeah, I understand.
And I'm not convinced that it would be.
Right.
In other words,
yes, well, right. In fact, precisely, you're right, because the following is true, and that relates also to my faster than light, space demons and all this kind of stuff, right? Because what that is, yes, you're right. It's closely related to space demons.
Right. Because the real question, yeah, if you had a rabbit where one eye was pointing on one side of the cosmic event horizon and one eye was pointing on the other, then in order for them to construct a coherent model of space, in order for them to construct a simultaneity surface, they would effectively have to perform a space-time completion.
Exactly. But we are microscopically performing space-time completions because we have,
because every pair of causal edges is a trivial cosmic event horizon.
Right. Which doesn't survive very long, but we're still having to, insofar as we are instantaneously creating a notion of space, we are completing across a temporary event horizon. But what would it mean? Okay, so there's got to be an analogy here. There's got to be an analogy with some kind of computer system where, why am I thinking of computers back in the day when you had docks for computers, where the thing had a docking station and then it had its notion of reality. If it's removed from its dock, so to speak, it has two separate notions of reality. I don't know why I'm thinking of that. It's like
or synchronizing. I'm going to channel Max here. It's also like synchronization of branches in a GitHub repository or something.
Yes, right. It's the forking. What happens if you live across two forks in a repository?
If you like, you can also take the example of a split brain patient, right? They have two different notions of reality.
Yes.
Right, but in a split brain patient, they're not necessarily synchronized, right? There isn't. Is there a synchronization procedure?
No, there isn't. So that's the thing. The connections which a healthy person has compared to them are like completions, and that completion gives you one notion of reality.
You mean the corpus callosum is implementing a completion?
Right.
Let's think about that for a second. I wonder whether I've ever spelled corpus callosum, and I don't even know how to do it. Is that the right spelling?
Yeah, I think it's right.
An operationalization of completion. So what you're saying is,
that's pretty fun. I like that.
Yeah, well, let's think about that for a second. Let's think about it. So, I mean, we can think about it at the level of society, right? Of completions with respect to different people having different. I mean, this is the Descartesian or whatever it is, kind of. In some sense, synchronization is achieved by, for example, what we're doing right now of having a discussion, so to speak.
Right. All human communication can presumably be thought of as some kind of synchronization of worldviews.
Right. Well, so then, a synchronization, aka completion. So this is saying. So then the question is, in my thing that I've been claiming for so many years, that there's no scientific way to think about consciousness, or that it isn't a useful thing to do. This is slowly slipping backwards into thinking about that, because basically what this is saying is, to be a valid observer, you need some notion of identity. That's the claim. That's a meta claim being made here. You need a notion of the fact that you have made integrated sense of the world. And this question of making integrated sense of the world, what is the relationship between that and some notion of something like consciousness? Because you say, the individual, in what sense? I mean, taking my favorite example of the weather.
This feels like a Xerxes question.
Yes, perhaps. Right. I mean, in taking that example, you've got all these different components. And you're making the claim that to be a valid observer, right, looked at from the outside, the observer must have enough completions to knit together these different branches somehow. I mean, it feels like, what does it even mean to have done those completions? Well, what it means is that the observer made a definite decision about what happened and acted accordingly. Because
yeah, so in some sense, what you're saying is that these a collection of these completions is integrating all the information about some scene that's being observed and giving a unified impression of that environment outside.
That's what I'm saying, right? And that's necessary to make a definitive decision, so to speak.
Right.
And that is the kind of operational definition of being a meaningful observer.
Yeah.
In other words,
that's not something we've kind of thought about before, or at least I haven't consciously thought about it before, of like viewing different bits of sensory apparatus as being, essentially different realities that your CNS is having to integrate.
Right. Right, but the point here being made is, in quantum mechanics, the big story is, when measurement happens, there's a definite decision, and then you go on, you make another decision, right? And this notion of a definite decision is this completion-based integration of these different branches. That's what has to happen in order for you to have an integrated notion of reality that allows you to make a decision. So, I mean, I guess my question would be...
I mean, so I actually had a slightly different formulation of it in the quantum mechanics. But I have a brief section of the quantum mechanics paper where I go into these slightly more philosophical aspects. And one way of formulating it that I came up with was, okay, if you take this definition of the observer as just being an object, some entity, some extended object in the multi-way system that has a recognizable identity that remains recognizable throughout some finite extent of time, then in order for the observer to have a single recognizable identity, they are having to perform completions with respect to their own internal representation. But then you can also say that the equivalence classes there, if the observer is macroscopic, and therefore if their internal representation of the world is stored at a macroscopic level, then the equivalence classes that they have to construct in order to in order to have a single well-defined identity will also suffice so as to ensure that basically the rest of the universe has a single coherent thread of time, if the observer is macroscopic and if they're kind of a statistically representative sample of the rest of the universe.
Yeah, I remember you making this claim. Let's take this claim apart for a second. So your basic claim is the observer, any macroscopic observer, and this is again going to be some ergodicity type claim, any macroscopic observer does enough knitting that in some sense they force the rest of the universe to be knitted.
Yeah, I mean, so your definition, which is a consequence of this one, I mean, they're not incompatible, but your definition requires the observer to be someone who kind of cares about what's going on outside. And my claim is that actually you don't need that. You can just have an observer who only cares about their own internal representation of the world.
Yes.
And so yeah, suppose the observer is macroscopic, the dynamics I've got
so claim, if the observer claim of Jonathan's, if the observer Jonathan's QM paper, if the observer is macroscopic,
and by that I essentially mean if the if whatever structure is encoding their representation of the world is a macroscopic multi-way system, then
if they have enough completions, to be coherent themselves.
Yeah.
Well, if they don't have enough completions, they wouldn't be an observer. They wouldn't be macroscopic in the first place, right? You wouldn't call it an observer. You're calling it an observer because it already has enough completions.
Yeah, precisely, exactly. So in order for them to be identifiable as an observer rather than just some random multi-way fluff.
So in that sense, a collection of completions itself is the definition of an observer. Let's say, let me rephrase that.
Yeah.
A collection of local completions itself is an observer.
Right. Which in turn is just a local coordinate patch of a branch-like hypersurface.
Okay, so the claim is right. So quotes, an observer can be thought of as completions that somehow knit together a local patch in a multi-way system, in branchial space, basically.
Right.
And I suppose then you would, if you want to say when is this observer conscious or not, in these terms, then you would say that when these completions are sufficiently are somehow in some sense self-generating, that not only are they completing themselves, but they can also in addition perform completions about the internal model of the external world, then that's intelligent or a conscious observer.
Right.
Well, conscious. Okay, so the claim would be conscious. I mean, these words are being played with here, i.e., conscious of what's going on around them.
Yeah, is when the set of equivalence classes produced by the completion is sufficiently general that that their internal representation of the world is effectively causal invariant.
Wait a minute. So I see. Conscious of what's going on around them means that, I see, there's a different way to say this perhaps, means that they remain causal invariant even when they are being buffeted by the facts of the world, so to speak.
And I think we could also stretch this argument a bit further by saying that that this consciousness in that sense is almost inevitable, because what would happen is that to exist as such, by definition, an observer simply has to be one who has managed to make internal completions. But because that system, what we call the observer, is inevitably having causal interactions with the world, at some point, in order to even make its internal completions, it is forced to have completions of things that interact with it. And that means a model of the world that interacts with it. So consciousness is almost forced upon in the process of the observer trying to just complete itself.
So long as the observer can complete itself. I mean, that's the question of whether there is essentially cohesiveness in the universe.
Right, or completability.
Right. I mean, so
essentially, this is a view of the observer as qubit, right?
In what sense? Well, wait, let me make a note here. I mean, so you know, can the universe be completed? Be completed / is it cohesive?
Right.
But when would you say there is no notion of completability at all? I mean, the only, so in the simplest way,
but it has, if you have one of these things and it's just it's splurting out, you know, it's just splurting out new branch pairs, and there's no way you can corral them.
Right, but at the axiomatic level, what would that mean? That when there is no way to impose any extensionality or univalence whatsoever, if you can't put any of that, then there is going to be an inherent incompletability.
I think so, but I think what that means is that if you end up with too intense a branching, which I suspect is somewhat related to this finite dimensionality of space. Well, if you end up, what's that?
Yeah, I mean, as I argued in the QM paper, it's the same but one level of abstraction higher, because the finite dimensional requirement that gives you the Einstein-Hilbert action, if you generalize that, you get a completability requirement that gives you the path integral action.
So what's the generalization? The finiteness plus?
So a straightforward application of the same extremization principle doesn't really work, because branchial graphs are in general going to be infinite dimensional. There's only a very restricted class of cases where they're finite dimensional. So you have to loosen the requirement of a finite dimensional limit. And the argument I made is that the natural loosening is a completability requirement.
All right.
So it's not saying that it is finite dimensional. It's saying that it can be made finite dimensional with a finite number of completions.
Right.
Which means it doesn't splurt out in branch pair. You know, it doesn't splurt out too many branch pairs.
Right.
Well, so the claim would be there exists a universe. In order to have a universe in which there can be an observer, in the sense of an observer, it has to be the case. Go ahead.
So yes, the argument that I made was that was exactly this: that if you have a universe whose dynamics are sufficiently ergodic, and where the observer is large enough that they are a representative sample of what's going on outside, then the equivalence classes they construct will be more general than they actually need to be, to the extent that they are forced to remain causal invariant even when buffeted by facts in the external world, which is why I said observer as qubit as a sort of nice encapsulation of that.
What would explain that? You mean qubit as in they are there?
Well, a qubit is again a unit, is exactly the same thing. It's a unit of quantum information whose identity remains identifiable throughout its dynamical evolution. So it also gets buffeted by the outside world and undergoes decoherence.
But by the way, we did add to the winter school list of projects these things about quantum observation frames and making realistic families of quantum observation frames.
Yes, although it's under the more general discussion of relationships between foliations and updating orders on digraphs and things.
Why don't we have a specific one, a specific project suggestion about quantum observation frames? Seems useful to see whether somebody can think
how
of
would one do that project without doing the more general case?
by thinking about what the analog of an inertial frame is. What is just a particular example of that? Just like you don't have to understand general relativity to understand special relativity. What is the analog of special relativity in the quantum observation frame case?
Right, but we don't know what the analog of special relativity is in the special relativity case.
What do you mean?
We don't have a formalization of what it means to be an inertial frame.
No, we don't.
So my question,
okay,
how do you do that? How do you do the quantum observation frame project without doing the more general project?
Well, I guess because I was thinking of a more physical intuition type version of it, rather than the version where you're actually looking at the multi-way graph. But fair enough.
Sure. I mean, we could have a kind of brainstorming project of what are reasonable quantum observation frames, if that's what you mean.
That's
Okay.
what I mean. Right.
Yeah,
I think that would be useful because, I mean, we know the qubit case. We don't really know other cases.
Right. No, I agree.
Any other cases?
I doubt it.
Right.
But I don't think that's a project in which we can make really good technical progress until we understand the causal case.
No, I agree with that. But I think we can make, insofar as, that people could make progress thinking about black hole entropy and things without having a technical understanding of, the quantum mechanics of black holes, so to speak. There's probably a way, in terms of people with, buckets of material going in and out of event horizons and so on, there might be a way of understanding this in that same sense.
Right. And actually, we should be able to instantiate toy cases of that, because if someone has a good formulation of a quantum observation frame, then they could, they can run a quantum multi-way system or something and actually construct it.
Yes. Well, I mean, the other point is, the other reason we care about quantum observation frames is that, well, a couple of reasons. I mean, first of all, that is potentially relevant. Right now, our model for probing quantum mechanics experimentally is based on this measurement idea, is based on the idea of essentially definitive measurements that are like quantum black holes.
Well, I think there are two avenues, right? There's measurement complexity and there's entanglement rates.
What do you mean?
There are observational consequences of maximum entanglement speeds.
Yes.
And there are observational consequences of non-zero computational complexity of measurement. And I think those are the two, as far as I know, those are currently the two main avenues to, observational predictions for the QM formalism.
Yes. No, I agree. I mean, I don't know how and how those show up in my system has too short a coherence time. That's the question is do those both show up in the same, what is the experimental, and in fact we perhaps should add this to our, what's the at the level of a quantum computer or something like it, what is the consequence of maximum entanglement speed?
Right. I mean, it puts additional physical limits on the execution time of circuits.
Right. Although circuits are usually not represented in, well, yeah, right. Yes.
They're not conventionally represented as extended objects in branchial space because there isn't a notion of branchial space. But they are inevitably extended objects in branchial space in our representation of it.
Right. Well, but by which we're basically saying that the working out of all the possible paths of execution of the quantum circuit, or alternatively the Hilbert space, so to speak, as representing the quantum circuit, gets to be a certain size, which is its extent in branchial space, so to speak. Right. I mean, okay.
Which, by the way, is not that dissimilar from the supposed topic that we're meant to be talking about. So if you have a Hilbert space, it is conventionally thought that, unlike in a space-time, there is no limit on, information propagation speeds through that Hilbert space.
Right.
But actually, we kind of know, both from our models and actually from more general quantum mechanics stuff like the Margolis-Levitin bound and things, that that's not really true. There is a maximum information propagation speed. That's suggestive that there's a higher order, there's some additional mathematical structure that's like a Hilbert space, but where there's a maximum information propagation speed.
Right. So what would that be in the case of Lorentzian space in ordinary space-time?
Yeah, I mean, so this is the point I brought up at the at that emergent space-time discussion, right? That Lorentzian spaces are nice because they're time-extended versions of Riemannian manifolds. There isn't, as far as I know, a mathematical. I asked this to Sean and Faye and people, and they didn't have answers. There isn't, as far as I know, a sort of time-extended version of a Hilbert space.
Add this to our list of projects.
Right. Okay. Again, I felt like this was a project that's kind of hard to do without a certain amount of technical infrastructure that doesn't yet exist.
Well, I know, but somebody could think about that question of whether there's there may be an obvious toy Hilbert space that has this temporal extension thing.
Right, but if you had a time-extended Hilbert space, then you could define a conformal structure on it, so that again, it was you were limited to 45-degree entanglement cones.
Indeed, absolutely. Yeah.
Sorry.
Yes, that's a good point.
Right, but then the point I was making was that actually, okay, so then in CQM, your picture, your Hilbert spaces get replaced with category, you replace the normal picture of Hilbert spaces with this FD Hilb category of finite dimensional Hilbert spaces. And so then I would assume that the same object we get when thinking about kind of complexity theory informed versions of categories would be exactly the object you would get by taking an entanglement speed informed version of a Hilbert space and categorifying it.
Yes, I agree. Right, but by the way, this general project relevant for the winter school would be essentially take any, we know how to take Euclidean space and time extend it to get Lorentzian and Minkowski space, right?
Right.
What other spaces? I don't even know, for complex projective space or something like this. What is the time extended version? Is that twistor space or something, the time extended version? I don't really know.
So a complex projective space is already time extended in the twistor space picture. And the whole the purpose of the Penrose it's quite interesting from a mathematical standpoint. So if you take a complex projective force space and you apply something like the John transform or the Radon transform to it, you get back to a real space. But that space has a weird metric signature that doesn't actually align with the Lorentzian signature. And the Penrose transform was specifically invented to fix the metric signature, so you got distinguished space and time directions. I
see. So in other words, it's a decomposition of complex projective space into something which looks like space plus time.
Exactly. Yeah. So like if you just did a Radon transform, you would get a plus plus minus minus metric signature, and the Penrose transform fixes that, so you get a plus 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 minus signature.
Right. But so we can imagine a different case where you just take any old random space and you ask its temporal extension and see whether you can get, what does the temporal extension of J random space look like?
Right, exactly. And there should be, I mean, again, I hate to bring it back to category theory, but there should be a categorical way of thinking about that, because basically, I think if you can describe
it's like a functor. I mean, the time extension is like a functor.
Right, exactly. So whatever the functor is that maps from a Riemannian manifold to its Lorentzian extension, there should be some kind of duality that lets you extend, lets you generalize that functorial map to arbitrary spaces.
One would think that's kind of the point of category theory, is to make those kinds of generalizations.
Exactly. Yes.
So then what is the functor that takes you from Euclidean space to Minkowski space?
I don't know. This is what this hypothetical winter school student would have to figure out. I don't know. Right. Xerxes, do you have any ideas?
I don't know what the functor is, but in practical computations, one would do a Wick rotation. So you need a functorial generalization of a Wick rotation, or at least to check under which conditions is such a rotation well defined.
Yeah, which is a total mess. I mean, the notion, well, in the practical, in the trenches quantum field theory, the validity of Wick rotation is a total mess.
Exactly.
Right. But so,
But it's a mess because it's not well defined. It's not a mess because it's it has the right intuition. It's just that one still has to identify the constraints under which it is well posed on that structure.
Yeah, but I mean, for us, if we look at our causal graph, which is defines a partial ordering, then to discuss a Wick rotation is to turn that causal graph into essentially a spatial graph.
Right.
That's what it would mean. Is where, yeah, that's an interesting question. What is the, I mean, a Wick rotation attempts to define.
Okay, I would argue it's swapping branchial graphs and spatial graphs.
That's not the traditional Wick rotation. I agree that that's an interesting case. But here, let me give a different example. What class of graphs have the feature that they can be created as causal graphs, as partially ordered, as directed causal graphs? Right? You could imagine you have Euclidean space. I mean, okay, you're doing lattice gauge theory. You have this Euclideanized space-time. And then you say, oh, under what circumstances are the field configurations that I'm getting ones that could exist in the, I mean, like for example, imagine that you have a propagating wave, which of course doesn't happen in Euclidean space. I mean, in other words, you're saying, of the things I see in Euclidean space, which ones, when do I get Euclidean spaces that can reasonably be Minkowskified? Were you saying something different, Jonathan?
Well, no, I don't understand why that's not the conventional Wick rotation, because in the canonical sort of decomposition of these things, you would say, okay, I have I have the causal edge distances that are giving me negative contributions, negative eigenvalues of the metric. I have space-like distances that are giving me positive eigenvalues of the metric, and I have branch-like distances that are giving me imaginary values of the metric. And what the Wick rotation I assumed was, my understanding of it is that it's just encapsulating the imaginary eigenvalues into the definition of the time-like direction, so you get a Euclidean signature.
Well, that will be a very interesting generalization of Wick rotation, because actual Wick rotation is simply Euclideanifying Minkowski space. Nothing to do with quantum mechanics. I mean, what you're defining is a very interesting generalization.
But this is not. But this doesn't even have to be explicitly quantum mechanical. This is just how do you go from an arbitrary metric that has positive, negative, and imaginary eigenvalues?
Yeah, I get it. Right. But I think there's a different thing, that given that we now know, okay, so this is an important point. I mean, given that we now know that there's, branchial space and there's physical space, right? The thing that has previously been done is to treat the time-like direction with respect to space, to merge together the time-like and space-like directions. So we have two new things to do. We can merge the branch-like and time-like directions, and we can do something crazy with the space-like and branch-like directions. And these are all forms of Wick rotation.
Right. And my claim is that the most conventional form, where you're just incorporating, you're just including the, minus I tau dependent in the definition of the time-like directions, is the same as switching the space-like and branch-like directions, and then swapping over the metric signature of branch time.
Well, that's a major claim. It might be true, but that's an entanglement of Wick rotation with quantum mechanics, which is just not something that's known.
No, but just on a purely formal level of how do you take this metric and how do you turn it into one that's Wick rotated? No,
I get it. I mean, that's a formal claim which has a physical consequence that says that Wick rotation has something to do with quantum mechanics, which normally it doesn't. But okay, but in any case, I mean, the thing that you're highlighting,
I would argue it does in the sense that in the way that it allows you to map quantum mechanics to statistical mechanics.
But here there's quantum mechanics because you're talking about doing it on the multi-way graph, right? If you're doing it only on the causal graph, then it's much closer to the usual Wick rotation without any quantum mechanics.
Right.
But what Jonathan is adding is this idea that the correspondence between quantum mechanics and statistical mechanics has to do with the swapping of branchial and physical space.
Right.
Well, it's an explanation for that, for the
I know it's a generalized Wick rotation that includes the statistical mechanics to quantum mechanics translation.
Right. It explains the e to the minus iht over h bar, coincidence.
Right.
But yeah, I mean, obviously, yeah. So you're obviously right that in the other way you think about it is you just swap the signature in the decomposition of the causal graph.
But I want to come back to our original thing. So the original thing had to do with this computationally bounded category theory.
Well, actually, I'm now quite optimistic that this Hilbert space picture would be one way of getting to that object.
Yes, I understand. I mean, so what you're saying is the computationally bounded. I mean, or the what is it? It's sort of evolutionary Hilbert space is really what it's about.
Right.
I.e., what is to Hilbert space as Minkowski space is to Euclidean space. And then, why does that? I mean, why can't we use the example of Minkowski space from Euclidean space to understand what's going on here? I mean,
well, I mean, again, at a purely formal level, you can. You just take the metric tensor on your projective Hilbert space and you add a negative eigenvalue or something. The question is, what does that do to these geometrical quantities? What does it do to your Fubini-Studi metric? What does it do to Fisher information?
Yeah.
What do things like entanglement monotones look like in that space? I'm pretty sure that's something no one's investigated.
Add it to our list.
Yep.
But
I think that will need. I suspect that will need someone with some expertise in things like information geometry, or
yes.
At least like complex projective geometry or something.
Okay, but this question about foliation functions, and I'm still looping on the whole consciousness business, and our notion of a being with identity as being operationally defined by something which has a coherent view of the world.
Right. But
so then I want to know, when, with that definition, when do our AIs have consciousness?
Well, this is why I brought up the qubit thing.
Go on.
Because I think there should be a kind of limit argument that you can make. So, in the ordinary way you think about quantum information, there are bits of quantum information all over the place, right? And we don't tend to sort of isolate them and identify them. A qubit is exactly a bit of quantum information that we do isolate and identify throughout its history.
Right.
Right. So it's like it's like the quantum analog of one of these observers. And so the point is that just as our observers are buffeted by external facts of the world that might cause them to lose their identifiable
coherence, right?
A qubit will undergo a decoherence procedure, essentially, unless it forms one of those kind of black hole-like objects that you constructed in your technical introduction.
Right.
So and the reason that those sort of black hole objects occur is because you get sufficient, there's sufficient convergence of geodesics. If there's enough convergence of geodesics, eventually you hit some analog of the Schwarzschild radius and you form something that's like a black hole, and then it's safe, then it's isolated.
By the way, that's another project for our list is black holes and branchial space.
Right.
Which we sort of looked at, but we haven't seriously looked at that. Mm-hmm. Another project, by the way, that maybe you already had was to extend the stuff that I did in that black hole searching bulletin, because I never got to the full quantum case of that. I never got to finding a realistic example of something where you could explore the interface between branchial space and physical space at a singular at an event horizon.
Right. I have a cheating way of doing that, but I don't think.
Okay, but anyway, let's go back to the qubits and observers. So, what's the analog between black holes and observers?
Well, but they're all the same thing, right? So, what is a completion doing? A completion is forcing multi-way geodesics to converge.
I know, yeah, right.
That otherwise would not have converged. And the statement that it is possible to perform an unfailing completion that forces causal invariance is the statement that there is effectively a Schwarzschild radius.
Right.
So that they're all basically the same. They're all situations where there is sufficient convergence of geodesics to ensure that a single object has a readily identifiable dynamical history. Because I mean, the black hole is the spatial case of that, because it's like, again, you generally don't say, here is a piece of space which has a well-defined identity. A black hole is a case where you do have a piece of space that has a well-defined identity, and the reason is because there's been sufficient convergence of geodesics that ensures
right
in the outside world.
Enough geodesic convergence to make an identifiable lump, so to speak, e.g. in space with a black hole.
But a lump that's not just identifiable, but it's somehow insulated from what goes on outside.
Yeah.
So that it remains identifiable.
But that itself would not be enough, right? Because you could even take, you could just call that a life process rather than consciousness, where it's just trying to maintain its identity. For being conscious, you'll probably need a little bit more where it performs completions that have something to do with some kind of unified information integration from outside.
Right. To be quotes conscious, it better be conscious of something.
Right, but my claim is that actually, once you have the former, you necessarily get the latter.
Because it has geodesic convergence, and the geodesics are coming from the outside world.
That's a geometrical way to think about it, but the sort of the logic way to think about it is this idea of, so just as, okay, if you have an automated theorem proving system, and when I prove certain critical pair lemmas, those critical pair lemmas don't just force those critical pairs to converge. They can force other critical pairs to converge. The critical pair lemmas can then be used in the proofs of subsequent things that were not originally related to them. Right. Precisely because the equivalence classes that I've introduced by computing critical pairs are strictly more general than what I needed to force the critical pairs to converge in the first place. And so in the same way, and so then the idea is that every time I add a critical pair lemma, it's a local thing. But because of this generality, if I add enough of these local things, eventually the global system becomes causal invariant.
Right. In other words, to have the being be coherent, that will force coherence on the outside world.
Right, but isn't there a point where such a transition happens from it being local to global?
Yes, yeah.
So it's not that you could call the being an observer or a conscious observer right away. There is a transition at which it happens.
In what sense?
Well, in the sense that initially, let's say right in the beginning, there is no observer. There's just fragments of states, and as completions are forming, some macroscopic identity is being formed, but that's not yet, at that point, it might not yet be sufficiently many completions so that it has even been able to gain some information integration of the world. But as this process goes on, gradually, not suddenly, but more like a gradual transition, it gets enough to form some kind of picture of the local patch around it.
Right.
And Xerxes, you bring up an interesting question about, essentially whether it's possible for an infinitely solipsistic being to be treated as conscious.
Well, I think it isn't. By the meaning of the word typically means it is conscious of things going on
that aren't its own internal processes.
Right.
Right.
I mean, I don't know whether that's but now, okay. So the question is, can we model this? Can we actually see? Go ahead.
I'm sorry, I just wanted to add to Zexi's point about the existence of a transition point from local to global. One sees the same thing in GR. So if you just have an ordinary star or something, that star is an object that is bounded in its kind of space-time extent, right?
Yeah. It's bounded, right. And for example, it doesn't get to see the whole history of the universe.
Right. But then as soon as you have, but once that star, if it collapses and crosses the Schwarzschild radius, and your trapped surfaces start to kind of stack, start to stack on top of each other, then suddenly that object, the black hole is no longer localized in space-time, because the definition of the black hole relies upon questions about divergence to future null infinity and things that essentially, so being able to define that being able to define that black hole as a single object requires you essentially to know the entirety of space-time.
Right.
That was the issue we ran into with these, doing searches for event horizons and things, that although you can find trapped surfaces and you can even find apparent horizons, finding an event horizon requires a strictly infinite amount of computational effort, because you need to know the whole future of the universe in order to identify it as an event horizon. So there comes a transition point where the structure goes from being localized in space-time to being somehow global in space-time, and that is the Schwarzschild transition point.
Well, so the basic claim would be, the space-time consciousnesses are the black holes, which have this sort of causal global entanglement with the whole universe.
It starts to sound a bit wooey, doesn't it?
It's very, very bizarre. but let's talk about the analogous thing. Yeah, I mean, clearly we do not have awareness of the whole universe in any particularly real sense. We're very junior consciousnesses in that sense. And we don't get to see the whole history of the universe, which a black hole does. At least ignoring,
Well, I guess the point is that if our consciousnesses didn't sort of eventually evaporate, in principle, we could
know about the whole universe.
We could ingest all degrees of freedom that there are to ingest, up to cosmic event horizons and things.
Well, so then the question is, okay, let's come back to the AI. Okay. So what is the definition? So in other words, if I'm going to measure, it's like people say AIs should have rights when they're conscious, whatever that might mean. How do I measure this? I mean, operationally, we kind of all know it has to do with, with this having a sort of a notion of a kind of continual notion of one's internal state, being able to integrate from the outside world. Those are all, those are standard kind of signatures of consciousness, so to speak.
Right, but I would argue that when one has an effective geometrization of branchial space and radial space, one should be able to compute explicitly what the Schwarzschild radius is in those spaces, right?
Yes.
And from that, you can infer how many completions do I need, in a particular local region, how many completions do I need in order to have in order for those completions to kind of infect the global system. And that gives me the transition point from unconscious to conscious. Okay,
how do we apply that to an AI?
Well, we have to break it apart and figure out how many, effectively how many completions is it performing, and if it's above, that number that's required for collapse.
I think operationally, what that means is it has to do with how much it can represent internally. Wait a minute. So, the universe has some number of degrees of freedom. We think maybe 10 to the 400. just to throw out a number. And clearly, a brain embedded in that universe does not have that number of degrees of freedom. So insofar as it has a meaningful representation of the rest of the world, it is some kind of minimized representation.
In a way, a black hole is the ultimate brain, right? Because if you look at this Bekenstein bound, which says that the maximum amount of information that can be encapsulated within a space is that the size of that is given by the radius of a black hole. And all, so in that sense, a black hole is the ultimate kind of
concentrator of information.
Yeah. So anything less than that,
just as it's also the concentrator of matter in a sense. It's a concentrator of, right. Go ahead. Yeah.
Yeah. So this idea of taking a black hole as the ultimate conscious observer is the most extreme case. So now, if you want to look at AI or even like animals or humans, etc., then you're probably asking how far away are these agents from what could be their potential Schwarzschild radius, and based on that distance, you kind of give some degrees of consciousness away from the perfect object, which is the black hole.
Although it's a little bit disappointing that the sort of philosophical sort of entanglements of consciousness are definitely not convincingly satisfied by a black hole. I mean, a black hole could contain 1 billion civilizations.
Yeah.
They just got ground up into the black hole. Boy, we go far away in these discussions. But I mean, let's bring it back for a second to actually, I want to bring this back to metamathematics and to understand what the analog. I mean, again, what is the analog of a black hole in metamathematical space? So we have the space. It's the space of proof space where we're proving theorems. What is the analog of a black hole in that space?
Well, decidability, as we've discussed many times.
It's kind of going the opposite way from what we're seeing in this other case. I mean, the space-like singularity is like.
Why is it? It's exactly what you'd expect, given what we've just discussed. I don't know why it's.
Explain.
Explain what?
I mean, you're saying decidability is everything gets figured out. There.
Everything can be figured out.
What's that?
Yeah, that everything can be figured out, which in the context, which more precisely means that, given a collection of points in a branch like, given a local patch in a branch like hypersurface, I can reduce them to a normal form that is the coherent picture.
Yes, but it feels okay. So what is a metamathematical consciousness?
Well, something that induces critical pair lemmas. It's an automated theorem prover.
Okay.
Right.
So this is
what is an automated theorem prover doing? It is constructing metamathematical black holes in order to convert arbitrary, non-normalizing, non-confluent, axiomatic systems into equisatisfiable ones that have confluence and strong normalization properties, which is what an observer is doing in quantum mechanics, just in a different context.
Okay, so the claim would be an automated theorem prover, or even a human theorem prover.
Right. Sure. Yeah, I guess.
A theorem prover.
In the sense that you can compile human theorem proving processes into collections of critical pair lemmas.
Right. Is generating critical pair lemmas, well, lemmas in general, but particularly critical pair lemmas, that induce geodesic convergence.
Right. Right.
And leads to decidable results.
Yeah. So essentially you have a sort of, you have the whole of metamathematical space, and here's my little decidable patch in which I'm going to do theorem proving. And I mean, I don't see why it's the opposite of anything we've discussed before. It's exactly the same as what's going on in, say, quantum mechanics, because you've got, there's this whole undecidable sea of complexity.
Right. The observer is
the decidable patch in that that's saying, I'm going to form this coherent picture of the world.
Right. The observer is forming a coherent picture, which might only be doable locally. Right? So in other words, there could be pieces of mathematical space that have this kind of rapid branching feature where it is very hard to have an observer there.
Well, we know that's true, right? I mean, Peano arithmetic.
Yes. But why isn't there something like Peano arithmetic? And there is. I'm not sure I buy that. I mean, there is something like Peano arithmetic in physics. It's like the observer is forming a coherent picture, which only might be doable locally. Okay, so in physics, where is it hard to have an observer? In mathematics, go ahead.
Well, I mean, these are the places where I would assume these are the places where you get strongly quantum phenomena, right? So the point is,
so an observer,
in mathematical space, right? You've in addition to these ones that automated theorem provers can kind of just solve by converting them into complement theories, you also have things like Peano arithmetic, where you can complete certain fragments of it, and you can have heuristics, and you can do approximations, and you can get closer and closer to something that acts like a decidable theory, but you can never actually get there. In the same way, you can have multi-way systems in multi-way representations of quantum evolutions, where you have patches that are non-completable, but you can kind of get closer and closer to something that's a classical picture. But the point is, you can't make it classical with any finite amount of computational effort.
Right. So the analog is something that is strongly quantum mechanical and not, i.e., not completable.
In geometric terms, that would be non-compressible. So you cannot compress the space to the point that the geodesics can be made to converge.
Yeah, that's true. But so let's talk about that in mathematics, because I'm not buying the Peano arithmetic case. You're saying, I mean, because Peano arithmetic, the question, we don't actually know whether most propositions in Peano arithmetic are decidable. Could only be some very thin set that are undecidable. I tend to think that's not the case.
Right, but actually that doesn't matter, right? If you took Peano arithmetic as your local patch of mathematical space, there, as I say, there are fragments of it that we could certainly convert into complement theories, but you can't convert the whole thing into a complement theory.
Sure.
That's all I'm saying.
Well, so what's the analog of Peano arithmetic in physics? What are the things that are never fully classicalizable? Do we know them?
Well, I would argue that you would get something like that happening at an entanglement horizon, right?
Yes, I agree.
There are places where you're forced to have quantum pictures of the world. Just as in metamathematics, Peano arithmetic is a case where you're forced to have a non-confluent system. Or at least you're forced to work with a system that's at least partially non-confluent.
Right. Well, okay, so an example is an entanglement horizon, but I wonder whether there are other cases that are a little bit more familiar than entanglement horizons.
Yeah, no, I agree. There must be, but
Okay, another project for our list.
Right. Brainstorm. Yeah.
When are things not classicalizable? So, I mean, the usual notion is, the coherent state formalism, for example, is like you go to high occupation numbers, and then in quantum field theory, and then you have something which is like a classical limit, where you have an eigenstate of the creation operator, for example. I bet there are cases that involve fermions where you can't do that because of the fact you can't go to high occupation number, because that's the thing that makes you not sensitive anymore. At high occupation number, who cares what the occupation number is, and who cares that it's quantized? I bet there are things here where it is forced to be. And I remember that there's a, I mean, by the way, do you have any things on your winter school list about the interpretation of fermions and the whole question about, this whole idea about trees versus grids as the story of fermions, and this notion of.
So on project 12 on the theoretical physics list is prove a spin statistics theorem, e.g. in terms of resolving versus non-resolving branch pairs in Wolfram model multi-way systems, and explore connections to the Dirac equation.
This is a very ambitious project for 2 weeks. Well, okay, fair enough.
So
okay.
maybe another example of what you just mentioned regarding systems that are non-classicalizable would be when you have the collapse of a star to a white dwarf or a neutron star. That system is forced to be quantum mechanical. There is no classical analog of it.
Well, a neutron star, that's true, but that's because of the exclusion principle. That's a fermion's game.
Right.
Now, in some sense, in this interpretation of fermions, where it is, this all comes together, right? Because the idea of fermions being the sort of tree-like thing that's not completed, that's not confluent.
Yeah, the high occupation number limit when you have an exclusion principle is exactly the limit as you have an infinite number of branches, and that's exactly the case in which you get non-completability.
Right.
It all makes sense.
It does all make sense. It's very exciting, really. Let's think about this for a second. So I mean, okay. But so the analog of strongly quantum mechanical in mathematics, again, these cases where, so what is a good analog of that? So in the case of physics, it's these fermion systems that don't have confluence.
Right.
What is the analogous thing in mathematics?
Well, I mean, so again, going back to the piano axioms, it's ultimately things like the induction schema, which force non-confluence, right? Or non-completability, I should say.
Let's be more precise. I mean, so in other words,
what's not precise? I mean, if we take the fragment of piano,
I understand. We take piano, then it's decidable without the induction axiom.
Right, which means that there's nothing preventing an unfailing completion procedure from terminating. So the point is that when you take that, if we take that higher order axiom and we reduce it down to something that's first order or equational using the procedure that find higher order logic proof does, then that produces a schema that is a generator of critical pairs, one for each possible proposition, at least one for each possible proposition. So that when you quantify that over an infinite domain of discourse, you get an infinite number of possible critical pairs, and they can't all be made to converge.
No, I understand. So the statement that you're making there is when you have an axiom schema that's splurting out branches, basically, then that's an example. So let's try to be a little bit more. Okay, so the question is, what is the characteristic of an area of mathematics that involves axiom schemas rather than axioms? And it's basically a higher order story.
Right.
It's when, what makes math non-completable? Answer, it's kind of things like, it's sort of necessarily higher order stuff, like axiom schemas. Now, but what is the analog of that? I mean,
well, Sorry, just to clarify that. So in terms of making a connection between that and the standard way people think about mathematical logic, this is then going to what you're basically saying is once you're at the second level of the analytical hierarchy, which basically is the transition point from algebra to analysis, or from algebraic theories to analytic theories.
You mean quantification over functions?
Right.
I.e.,
the sort of, this is obviously, there are plenty of exceptions to this, but as a general philosophical principle, algebra is, algebraic theories can be formulated in terms of quantification over natural numbers, and analysis can only be formulated in terms of quantification over functions of natural numbers.
Right.
And then, again, plenty of exceptions, but then topological theories often require third order logic.
I actually didn't know that, but that's not surprising. Quantifies over functions. And then I see it's topology is quantifying over function spaces.
Right, exactly. So actually the back when I was doing axiom curation, I was looking around for examples of third order axiom systems. The only one that I could find that anyone actually used were the axioms of, general topology.
I see. So, but so let's just think about this. So this is saying, so the claim being made is fermionism, so to speak. What is the analog of the exclusion principle in mathematics? It's going to be some non-completability statement, because okay, these higher order quantification things, okay, the intuitive sense is in a sort of tree-like fermionic system, you keep on going off in different directions. You keep on being able to generate branches in different directions. And in some sense, that's what's happening when you have these higher order quantifications. You keep on being able to, you keep on sort of wanting to talk about things that go off in other directions, in the sense that if you are, that's very qualitative. Did that make any sense?
Yeah, as I was saying, you have when you have, say, the axiom scheme over induction, each one is generating at least one branch pair. Each instance of it for a given proposition is generating at least one branch pair.
Okay, but so what's the analog of the exclusion principle?
Well, the exclusion principle, to the extent that we understand it in multi-way systems, which is basically not at all, relies on interplays between branchial geometry and spatial geometry.
Yes.
Because it's placing limits when you have branch pairs that are non-converging, it's placing limits on, how close together the associated degrees of freedom can be and things like this. But that
no, we don't have an analogous spatial geometry.
Right.
Well, or do we? I mean, in what sense is there, we've discussed this before, is there forced cohesion in metamathematics?
Right.
In other words, does the existence of, and so probably the very existence of these higher order theories goes against cohesion, because it's just splitting out branch pairs.
Right.
In other words, the geometrization of metamathematics, the presence of higher order theories goes against geometrization of metamathematics.
So what one would expect in the most naive geometrization is, okay, so if we have a decidable theory, like group theory or something, if you consider geometrizing metamathematical space in terms of something like proof complexity, right? So we have two expressions in group theory, and their separation distance is the proof complexity of the, associated with the proof of their equivalence.
Yep.
Then in that case where you have where the theory can be made decidable and therefore can be made where the theory is decidable and therefore can be made confluent, you can construct kind of neighborhoods of arbitrary size. So I can say,
yes.
Given this expression, I can have, given a fixed proof complexity, I can have an unbounded number of expressions that are kind of provably equal to that one within that given proof complexity. But in the case where you have an undecidable theory that cannot be made confluent, presumably that can't happen.
Well, you have horizons basically in that case.
Right. Which so you effectively, and that I assume is some kind of analog of the exclusion principle, where there's a bounded, given an expression in Peano arithmetic, there are only a bounded number of expressions that you can prove are equal to it with any finite complexity.
I see what you're saying. So the analog, yes. I think that's right. So the point is, yes, that's right. The point is, fermions are, effectively have horizons in branchial space. That's what it means to be that. That's what that branching thing is doing. And so then decidable fragments in mathematics have horizons between them. So it's saying the exclusion principle, yes, the exclusion principle is the same statement as there are an infinite number of large cardinals, so to speak. So in other words, that Peano arithmetic is not. So the analog of the exclusion principle would be there are an infinite number of distinct axioms that could be added to Peano arithmetic. And they don't somehow none of them can kind of occupy the same space. If that makes sense. In other words, each separate extension of Peano arithmetic gives you a different, the claim would be each separate extension of Peano arithmetic gives you a distinct set of new theorems. And that's the analog of the fact that every different sort of fermionic space has to live in a separate region. Does this make any sense? I think something like this is right.
Yeah.
So, again, the exclusion principle says that these fermions cannot consistently be thought of as occupying the same space. This is saying these different, the adding the new axiom is kind of like putting down that new fermion branch, and it can't consistently be completed into occupying the same space as some other branch. Something like that. So where does this leave us on? So this is saying, in that sense, we do not have cohesion in metamathematics. But within one, I mean, there can be larger areas of mathematics that aren't in their own separate event horizons, that aren't separated by event horizons. So the question is, what we're saying then is that like if there's an Einstein's equations for metamathematics, oh boy. Yeah. This is yet another iteration of this stuff. I mean, yeah, well, maybe it's getting late here. We didn't manage to fully explicate our computationally bounded category theory, but we are making interesting progress here. Did we exhaust you guys? No way.
No. But yeah, I coming back to the original topic, I think this approach of just taking a quiver where the directed graph is weighted, and then defining a restriction structure that's compatible with the weighting, and then constructing higher order variants of that category. I think this is the general. It's a general way of constructing what we want.
Right.
Because then the degree of computational irreducibility is quantified by the degree of failure of compositionality, which is in turn quantified by the essentially by the additive properties of the of this higher order composition operation that acts on these weighted arrows.
Yes, that's one way to think about it. I mean, to say, but I mean, I'm not really understanding the need for the sort of the get lost arrows.
Well, because otherwise you're not formalizing Turing machines, or you're not formalizing universal Turing machines.
Yeah. I mean, unless you imagine
having a category, having a non-small category with infinite paths.
Exactly.
But then, as I say, that requires us making a philosophical choice about how we treat partial functions and whether we treat the disconnection and infinite path cases as distinct.
Which I think we should. So which way does that imply?
Well, it implies that we need both infinite paths and disconnection, and the disconnection would be having these get lost things.
Right. I just don't think the disconnection case is all that interesting. I think that the disconnection case is not necessarily related to the get lost case, as it isn't in combinators, for example. There is no disconnection in combinators.
Okay, I take strong issue with that statement, but
I think there isn't. I mean, I think it's like a multi-way graph, as you said. There isn't disconnection in multi-way graphs except in pathological cases.
Yeah, sure. As a multi-way graph, there's no disconnection, but in a partial combinatory algebra, you absolutely have a partiality structure. You have a restriction structure.
No doubt, where you can't get from here to there. No doubt. But
right.
Which one are we concerned about? I thought we were concerned about
the point. I agree with you in the sense that I think multi-way systems are a better way to think about it, in the sense they give you a more refined view. The point that I'm just making is that the standard way of thinking about partial combinatory algebras can essentially be rethought in the context of multi-way systems by saying, okay, actually, we don't need a restriction category. We can have a category that doesn't need a restriction structure. It just allows for the existence of infinite sequences. Infinite sequences of morphism compositions.
Right. But the thing that was the original idea from yesterday had to do with this notion that the concept of growth index hypothesis, of the necessary geometrization of the infinity category or whatever, infinity topos, whatever it is, that is a consequence of the fact that to get to that point, you have to have reached sort of the PCE level, which means that it is inevitable that you have computational irreducibility, which means that it's inevitable you have a certain kind of ergodicity, which means that it's inevitable that you have a certain kind of, in a sense, uniformity to the system. And then yeah, well, that's interesting.
Right. And so you know, the place where that gets kind of interesting is where, okay, so obviously as we know, if you have an undecidable theory, unfailing completion doesn't halt. So you get an infinity, you can do an infinity category construction. So that's all fine. We know that undecidable theories should be weakly ergodic because of computational irreducibility. The interesting implication of this whole line of reasoning would suggest that there should be essentially a dynamical systems characterization of the mathematical theories that are decidable, but for which unfailing completion doesn't halt. Namely, they're ones which are not universal, but still weakly ergodic.
Wait a minute. Unfailing completion. Wait a minute. The case you're saying, you're saying mathematical theories for which unfailing completion does not halt, but where they are decidable.
Right. So those are cases where you get an infinity category, right? Because the completion procedure doesn't halt.
Right, but it's some kind of non-PCE. It's basically, look. This is the classic case, right? Because the classic case is, let's take Rule 30 for example. Either it's computationally irreducible, there is no characterization, or there is a characterization and it's a new field of mathematics, basically. Right. In other words, either there isn't a way to crush it and make it reducible, or there is. But right now, we don't know any way to do that. And what we might imagine is that there is and this is related to this whole decidable fragments with horizons between them. How broad, how much mileage do you get from one new piece of reducibility?
Right.
So, this question, okay, it's like, let's see. So you're saying, okay, so your question way back here was,
what are the decidable mathematical theories for which unfailing completion doesn't terminate? As I say, there doesn't seem to be any, abstract rewriting or mathematical logic characterization of those theories.
No, I understand.
The exciting thing is that there might be a geometrical or dynamical systems characterization.
No, I understand. What is the characterization of theories where unfailing completion does not terminate, but in fact, the theories are decidable? Yeah, this is so typical of you have an analysis method and it doesn't get everything. Right? And then the question is, then you need a new analysis method, right? So unfailing completion doesn't terminate, but where maybe some other completion method, maybe some other approach would terminate.
Yeah. But you see the point I'm making, right? If Grothendieck's hypothesis is true, this tells us something about this characterization.
If it's generally true, if it doesn't fail for these ones.
Right. So the point is we should be able to either prove or disprove Grothendieck's hypothesis for this particular construction.
I understand.
By essentially, so what you would expect if Grothendieck's hypothesis is true is there are non-universal computational systems that effectively simulate ergodic systems to arbitrary degrees of.
Yes, I understand. I bet this is going to prove it's not true. I bet this is going to prove that there are exceptions to it.
Really? So you reckon that these theories will not be ergodic?
That's correct. Or they'll be ergodic and only in some very boring sense. They'll be like linear feedback shift registers, for example. They will be nominally ergodic, but have lots of regularity.
Fair enough. In which case, that opens up this more general question of what is the what is the hierarchy of ergodicity versus geometrization requirements?
Exactly. For some kind of geometrization, you probably only require some very, ergodicity is not randomness, so to speak. Ergodicity is a weak, linear feedback shift registers have, uniformity. They just don't have cryptographic randomness.
Right. So you can define a spatial structure of LFSRs, but not a very exciting one.
Well, the issue is, what if space? Yeah, I mean, that's the question. The question is, what if space wasn't really ergodic, wasn't really wasn't really microscopically irreducible.
Right, and so then what you'd expect is that,
but was somehow equipartitioned or something, equidistributed or something like that. In other words, it's like Champignon's number as opposed to pi. If that makes sense. So what if space was like Champignon's number?
Yeah, and as I was saying, what one would expect in that case from the standard geometrization arguments is that you would obtain a locally Riemannian metric, which degenerated essentially to a Manhattan metric on large scales.
Possibly.
Right, because the point is that the weakest of ergodicity requirements. Okay, if you think about these objects, and if you think about LFSRs or whatever, and you evolve their causal graphs, what the weakest ergodicity requirements are telling you are, that they're placing constraints on fluxes of single causal edges through hypersurfaces in that graph, and stating that the average flux through a given hypersurface goes to 0. Right.
Yes.
But then that's only a very local characterization, and if you had true algorithmic randomness, as in the pi case rather than the Champignon case, you would expect that not only are the fluxes of individual hyperedges, individual causal edges, not only do they sum to 0, but the fluxes of particular causal structures should sum to 0.
Right. Well, that's the notion of
that's electric charge versus gravitational charge.
Look. I think what this is how realistically are we emulating the continuum? Because I claim the continuum is
that's just what it means to be geometrized.
Well, I understand that, but I'm saying the continuum, what it was. I think we're saying the same thing. If you make something which is a bunch of stripes, okay, you can be distributed to every point in space, but you are not going to have all the correct limiting properties of the continuum.
Right, and I'm giving a formal definition of exactly what that means.
Say it again.
Well, okay, so the weak ergodicity in the sense that we've defined it, for instance, in my relativity paper, is the statement that if we pick an arbitrary hypersurface in the causal network, the flux of causal edges through that hypersurface for any given hypersurface sums to 0 in the continuum limit, right? The net flux. That's what the weak ergodicity is. If we then, just like
wait. So Jonathan's definition of weak ergodicity is essentially isotropy, is statistical isotropy of causal fluxes.
Right. And so just like in the transition from the construction of gravitational charge to electric charge, where one is no longer considering single causal edges, but it is considering finite collections of causal edges with certain topological features, you can similarly define stronger versions of ergodicity that consider not fluxes of single causal fluxes of these larger topological features. For a truly algorithmically random system,
any such things, right?
All of those fluxes will sum to 0,
right.
but not in something like not in a Champignon case.
Right. Individual edge causal fluxes, right? And the question is there any general case? Look, the general case is there a true notion of space without particles? Because that's what it's saying, is to say that there is that there's a notion of space, which is the same kind of thing as saying that there's a continuum, is to say the whole thing is not made of these lumpy particles. It's really, in some sense, sort of completely random and not made of a identifiable collection of topological obstructions or whatever else. Does that make sense? I mean, in other words,
that's the point, right? That each of those if the net flux of all possible topological obstructions goes to zero in any hypersurface, then there aren't isolatable topological obstructions that as distinguished from the background space.
Right. So the issue is there a notion of space which isn't made of particles?
Right. Okay. So anyway, so taking the formal definition that I gave, you can show that in the appropriate limits, the metric that one gets by smoothing over average distances between points on geodesic balls converges to a Riemannian metric as opposed to a Manhattan metric.
Fair enough.
But if those ergodicity requirements are violated, that may be true on a small scale. Okay, so suppose you had weak ergodicity but not algorithmic randomness, so that there were some topological structures where the net fluxes didn't sum to zero. So then if you looked at very local geodesics at the level of single causal edges or small numbers of causal edges, it would look like a Riemannian metric. But over larger distance scales where those topological features become relevant, you would get something that becomes progressively more like a Manhattan metric. And so you would start to see features of the discreteness.
I understand. I get it. But so what's this notion of space without being made of particles? What is the analog of that for metamathematics, or for the infinity groupoid, and so on?
So an object which is not made of particles, or in other words, an object which does not have an obstruction, is like an open set. Is like an open set, and this idea of asking a space without particles is saying that you have such open sets, and they give you a topological space.
Something like that sounds about right. I mean, that's basically saying there's a genuine continuum.
Yeah. So
there's a notion of continuum.
Right. Because a particle or a point would be what one would call a closed set.
That's a good point. Right.
So essentially, Grothendieck's hypothesis is saying that when you have the infinity groupoid, you don't have these type of closed sets. You exclusively have open sets, and that gives you the notion of a continuum space.
Yes. That's interesting. So, right. That basically.
So and I suppose in that way of thinking, this point that Jonathan just mentioned about certain spaces where locally they might still be Riemannian, but globally not, those might be thought of as saying something like this: that you have this collection of objects that don't have obstructions, which we could call open sets. Then the question is, locally you can glue them and together, and they might still give you the standard topologies or Riemannian topologies. But globally, if you're not able to have the right gluing conditions, then globally it will still not give you a proper Riemannian type of topology. So there are two things that one needs. One is the existence of these obstruction-less objects, and second is a gluing rule for them. These two things together will ensure that you have a continuum space.
Yeah, sounds about right. I mean, so again, this.
So for us, I suppose the question is, what do these obstruction-less objects correspond to in meta-mathematics?
I don't think we know what particles correspond to in meta-mathematics.
Yeah, but instead of trying to define a particle, if we define this object, then the particle can be thought of as some complement of this.
Well, yes. I mean, intuitively, one would think that the continuum is where there are infinitely close theorems.
This is why I need to publish that computational complexity preprint at some point of the article.
Because
then I think it would be a lot less confusing, these kinds of things.
Because you figured out what?
Well, because the main result, as I mentioned, whatever it was, back pre-summer school, that I'm not claiming to have sort of systematically investigated the relationship between computational complexity theory and multi-way systems, but the one theorem I was able to prove was this relationship between polynomial time reductions or X time reductions and quasi-conformal diffeomorphisms between branch-like hypersurfaces, right? So then in that construction, the X complete problems, like the NP complete problems or whatever, which are the things that obstruct you from being able to make those quasi-conformal diffeomorphisms, become exactly the topological construction, the topological obstructions. So the particles in that complexity space become like NP complete problems or X complete problems. And so then if you did the same thing in metamathematics, you're then talking about transforming between different axiomatic systems and modifying proof complexities. And if you have if you try and make like a polynomial time reduction of one axiomatic system to another, there will be certain collections of theorems whose proofs are like the analog of NP complete proofs. And they will act as topological obstructions that prevent you from making those diffeomorphisms.
Okay, so the claim is that the particles are like the X complete problems, where because they obstruct continuous deformations of branch-like surfaces.
When I make a polynomial time reduction of one problem to another problem, what is it that I'm really doing? Well, I'm making a smooth transformation between one branch-like hypersurface and another, right? Because the two problems are just two different ways of foliating the multi-way system. And the statement that it's quasi-conformal, the statement that it's not distorting angles by more than some bounded amount, is just stating that I'm not distorting the metric on that branch-like hypersurface by more than a certain amount. So in other words, it's a perfectly...
Right. So the quasi-conformality is quasi-conformal with respect to whatever, to the computational complexity class.
Right, exactly. So things like polynomial time reductions, exponential time reductions, etc. Those are all representable as quasi-conformal diffeomorphisms, but where the quasi-conformality bound is different. Mm-hmm. But then the point is that, okay, so what happens if I have what would prevent me from being able to make that smooth transformation? Well, it's the presence of a topological obstruction, right? If I have a topological obstruction, that's a place where if I can't define a quasi-conformal map in that neighborhood because it's going to have a discontinuity at the point of the topological obstruction.
Yeah, I get it.
Right. So I can't construct a smooth, nice smooth diffeomorphism.
I'm not quite sure what a problem looks like in this space. I mean, in other words, a problem. What is a problem if I'm sitting in a multi-way graph? A problem, what is it?
You mean in the computational complexity case or in the mathematics?
Yes, in the computational complexity case.
Well, a problem is what you're wanting to map one geodesic. Okay, if you consider a multi-way, the time extended multi-way evolution graph, mm-hmm. A problem is a mapping of one geodesic ball onto another in the time extended case, right? Because what you're doing is you're mapping a collection of inputs that I'm treating as being local with respect to some coordinatization to a collection of outputs.
Okay. Mm-hmm.
Right? A particular instantiation of a problem is a single geodesic. And then if we then consider, so if we consider, right, all possible inputs of the traveling salesman problem and all possible solutions of the traveling salesman problem, those form two geodesic balls, but at different, different time slices of the multi-way evolution graph. And so then the formulation of the problem is defining the paths of the collection of geodesics that maps from one ball to another.
Right. Fair enough. Okay, so it's a geodesic ball, right?
Instantiations of problems are geodesics, and problems themselves are geodesic, are pairs of geodesics.
Right. Individual problems are geodesics.
Right.
Individual instances, individual problem instances.
So then, if you look at the time evolution of one of those geodesic balls, you get to see that problem, evolving in time, so to speak. And if that geodesic ball happens to form a topological obstruction, the claim would be that it is it is an X complete problem with respect to the quasi-conformal diffeomorphism defined by X, because it's the thing that prevents you from being able to make an X time reduction from that problem to a different one.
Well, but operationally, there's this geodesic. I'm a little bit confused.
Well, no, okay, so just imagine we have this, we have a definition of problems in terms of just maps between geodesic balls. Mm-hmm. If you now imagine that the two geodesic balls at the beginning and endpoints also formed, non-planar tangles or something.
Yep.
Then you have something like an X complete problem. Right, because normally the geodesic ball, as it propagates, has no non-trivial topological properties associated with it that remain persistent.
So you're saying it's then equivalent to background space. The problem, if it isn't complete,
yeah, right, exactly.
It's equivalent to background space.
But if there's something that makes it identifiable as being distinct from background space, i.e. a topological obstruction, then those are the cases we're interested in.
Mm-hmm.
And so,
so wait a minute. Completeness of a problem means it's distinct from background space.
Right.
Okay. But then, hold on. The thing. Okay. So what's the analog of this in math?
Right. So the mathematical case is, if we now considered so suppose we had a field of mathematics that's defined by a collection of theorems.
Yes.
So that can also be defined as a pair of geodesic balls with paths connecting them.
Mm-hmm.
Right. And so then, if you look at suppose that field is I don't know, let it be homotopy type theory or something.
That's really a bad example.
Yeah. Okay.
That's going to get so encrusted. The theory of elliptic Diophantine equations or something.
Okay, fine. The theory of elliptic Diophantine equations. You formalize it using ZFC set theory or something.
Mm-hmm.
Okay. So then that theory has a proof complexity associated with it. It has an average length of geodesics. It has a volume integral over that collection, over that tube of geodesics, etc., from which you can derive a proof complexity.
Mm-hmm.
Right. Okay, so then you could ask. There are other possible axiomatizations of mathematics in which there's also a theory of elliptic Diophantine equations where the proof complexity is going to be different. So just you can talk about polynomial time reduction of problems in computational complexity theory. You could also talk about polynomial time reductions of the theory of elliptic Diophantine equations, where you reduce the we modify the proof complexity of the theory by no more than some polynomial amount.
Yes.
By switching our axiomatic systems. But the point is that there will be certain theories of mathematics which act as obstructions. So if we try to make a polynomial, if we try to sort of reduce, if we try to make a polynomial time reduction of all of mathematics by switching from ZFC set theory to some alternative axiomatization, there would be certain theories that would kind of hold out and prevent us from making that smooth transformation. They're the analog of the NP complete problems or the X complete problems in computational complexity theory.
I understand the claim. Let me try understanding it better. So you're saying as we transform our basis in mathematics, I mean, this is the meta-mathematical analog. transform the basis in math, e.g., change the underlying axiom system, what sort of changes smoothly with the underlying axiom system, and what becomes a holdout, I guess is what you're saying. I don't know what, I don't even know what on earth it means when you change the underlying axiom system. I mean, that's just not an operation one usually does.
Right.
Well,
the whole
might
point
have
is,
a situation. You might have a situation where you're, for example, in one setup you're choosing a particular law, like the axiom of choice, and in another you're not.
Oh, sure, but I mean, change of the axiom system in computation theory. Change of axiom system is like change of underlying computation. Is a change of underlying computation system. E.g., different kind of Turing machine or something.
Right. It's a change of description language, which is what one is essentially, when one talks about, polynomial time reduction, that's essentially what one's doing.
Right.
Yeah.
But in mathematics, that would be more like changing from algebra to geometry or something.
It depends what you mean by algebra to geometry. I would say it's more, it's more like, I don't know. I'm not sure what that statement means.
Well, I mean, it means that's a description language thing. It happens to be a decidable change. Or from ZFC to something else.
Right. But algebra and geometry are too broad to uniquely specify axiom systems.
Well, fair enough. Like changing from one axiom system to another. Sorry, Xerxes, you were going to give an example of when you change axiom systems.
Yeah, so maybe you say from classical logic to constructive or intuitionistic logic.
Right, but those are big jumps, sort of bigger than one gets the feeling that in computation theory that there's a bigger family of underlying potential machines. Although it isn't really true, in fact. I mean, there are actually a limited number of such machines. But, no, I'll tell you what the issue is. The issue is the encoding of the problem, like the encoding of the traveling salesman problem could change. Right? So maybe that's a...
but that happens in math too, right? The constructions of the integers are very different in topos theory versus ZFC.
Yes, I understand. But I mean, you can just encoding any given problem, even within one theory, even on Turing machines, encoding the traveling salesman problem. There are many different data structures for doing that.
Sure, but same in mathematics.
Explain.
There are many possible constructions of the natural numbers, even in ZFC.
I see.
I can do the von Neumann construction. I can do the Peano construction. I used to know all of these off by heart, but I can formulate it in terms of cardinals. I can formulate.
Yeah, right. In math, one can define an intuitive notion like natural numbers. Using different data structures.
Right, and just as with TSP, it's then like non-trivial to prove that they're all describing the same thing.
Right, but so by saying these different intuitive notions, the notion of a particle, what is an example of an X-complete problem in mathematics? So it's a problem which, with respect to these changes of viewpoint, changes of data structure, it's equally hard to prove. Well, no, it's the hardest problem. See, we don't usually have a characterization of these. We don't have the notion of computational complexity theory in metamathematics.
Well, we do. We have proof complexity.
Yeah, but I understand, but that's not been well explored.
Oh, no, I agree. It's a very underdeveloped field, but we can develop it.
Right.
But yeah, I mean,
to do. I mean, yes, I agree that that's the proof complexity. So this is saying, you know what it is? This is like, okay, the analog is CF, the commutativity in commutativity in the minimal Boolean algebra axiom system. That's what it's like, because that once you've proved that theorem, you've kind of broken the camel's back, so to speak. Then you can do a lot of other stuff.
Right, of course, because then your effective axiom system has the same expressive power with the same, expressive complexity as any other axiomatization. But the point of the lack of a smooth quasi-conformal diffeomorphism is that the proof of that initial commutativity result, or whatever it happens to be, is irreducibly large.
Right. So what you're saying is the particles are the difficult general theorems of a theory.
Right. So if you look at the computational complexity theory example, if I take all the problems in NP, and I make a change of description language, there are a bunch of them that I can map essentially to problems that are in P. But there are also a bunch that I can't, and the ones that I can't are exactly the NP complete ones, like TSP.
Right? Yes.
And so I can do the same thing in metamathematics. I can say, okay, there are a bunch of different theories of mathematics that have a bunch of these different theorems, of different collections of theorems. And for certain theories, I can change my axiom system and dramatically shorten the proofs. But then there will be other theories, other collections of theorems, which can't be shortened, can't be reduced to, a different proof complexity.
Right. So the question is to identify, let's say for arithmetic, what are the particles of arithmetic? What are the theorems in arithmetic that are these sort of irreducibly hard? What are the irreducibly hard theorems of arithmetic? Very interesting. I mean, and those, yeah. I don't completely yet understand this. So those are ones where the geodesic path, see, I don't quite understand this. I mean, those are ones in terms of proof complexity, where proof complexity is measured by length of geodesic path. Those are ones where the minimum length of geodesic path is long.
Right. There's no coordinatization or no smooth change of coordinates that makes those paths shorter than some bounded amount.
Right. It's not completely clear to me how that is analogous to the particle case in space-time.
Why?
Why is it? Well, why is a particle a
particle is also a topological obstruction that prevents smooth changes of coordinates around that point.
Yes, right. But I don't understand the geodesic length thing. What's the analog of the geodesic length thing for a particle, for a spatial particle?
Well, the geodesic length is only relevant because we're talking about quasi-conformal diffeomorphisms.
So explain that in the context of spatial particles.
Well, so if we also enforce the condition that our diffeomorphism, that our coordinate changes be quasi-conformal in space-time, then you'd get the same effect. That because in the vicinity of a topological obstruction, you are constrained in how you can coordinatize your foliations, right?
Yeah.
Because you essentially can't make a smooth coordinate patch that sort of intersects that topological obstruction. So that then if you wanted to make a quasi-conformal transformation of space-time, you could distort arbitrary geodesics in the background space, but you couldn't distort, there's a limit to how much you could distort arbitrary geodesics between topological obstructions.
Fair enough. Fair enough. All right, we should probably wrap up here because go ahead. You were going to say.
I was just going to say precisely because of the failure of weak ergodicity stuff that we were talking about before. The fact that I can make quasi-conformal diffeomorphisms that change the lengths of geodesics arbitrarily is a consequence of weak ergodicity.
Sure.
Because particles are local failures of weak ergodicity, they restrict the number of smooth transformations of geodesic lengths I can make for those world lines. And so in particular, of course, minimum and maximum geodesic lengths.
Yeah. So particles, coming back to the mathematical case, the failure of Grothendieck's hypothesis, if there is one, well, we said two slightly different things. We said one failure is, well, okay, if the world is made of trivial particles that all have sort of trivial topological structure, so to speak, then you just can't get space to be mixed up enough to be sort of cohesive and so on. And in a sense, in mathematics, okay, so here's a bizarre claim. If there are no easy problems in mathematics, in some sense, if everything consists of just these sort of topological obstruction things, if it's just a small number of hard problems and there's no kind of glue in between, then the claim would be that that will be a case where that is potentially a case. It's also a statement that computational irreducibility lives on top of an infinite amount of computational reducibility. Go ahead, what you can say.
No, but but the mathematical case is somehow even more obvious than the other cases, right? Because you're basically, if math only consisted of a small number of hard theorems, then the notion that it's possible to make continuous progress in mathematics, which is really the statement of cohesion in mathematical space, goes away, because you have to make these kind of repeatable jumps to prove these.
Right. And math consisted of a limited number of hard problems.
But the point is that the cohesiveness of mathematics ensures that actually I can prove kind of incrementally more sophisticated lemmas that mean I don't have to make those jumps in one go for most problems. But there are hard problems where I do have to make those jumps, and those are the topological obstructions.
And nothing else. Then there would be no incremental progress. No cohesion in mathematical space. In a sense, no continuum. I mean, that's the same thing as if physics consists of a limited number of particles, there will be no continuum space, which we already know. That's the case of a rarefied gas, basically. We don't have a continuum. We don't have a continuous fluid if we only have a small number of particles. So I think it's the same thing. The notion of incremental progress in mathematics is, so in computational complexity theory, let's see, the analogous thing is, right, the claim is the existence of computational languages is a consequence of the fact that not everything is just a limited number of hard problems, that there are hard problems that become the built-in functions of the computational language, but there's a lot of other stuff in between. If it wasn't for that, there would only be the question is it worth having a computational language? Or do you just need a special purpose, or just a special purpose thing that does that solves a particular problem, so to speak? That's just
so in a way, this language is an example of an open set, right? Because what it's doing is it's smoothing over the hard problem, and it's smoothing it in a way that now this open set can connect to other open sets and build a continuum of connections.
Yeah, that's true. That's true.
And so in some sense, what Grothendieck's hypothesis says becomes sort of obvious in these terms, right? Because if mathematics was just a bunch of hard problems, that would be just like a small finite set of discrete points, and that's not a continuum. But what Grothendieck's hypothesis is saying is that when you have enough morphisms at infinite hierarchies of homotopies, then you eventually will reach a topological space. So it almost appears obvious then.
Say that again. I mean, because.
So over here we are thinking about these hard problems. If we think of them, the hard problems in mathematics as discrete points, and discrete points do not form the notion of an open set. You cannot do anything else with them.
Right.
But on the other hand, if you had these languages which are like open sets and you have a collection of them, then you can start gluing them and building continuum spaces out of that. So in a sense, what Grothendieck's hypothesis is saying is that when you're able to construct an infinite hierarchy of morphisms in a homotopic sense, you'll eventually reach a point where you get a continuum space.
Right. But why is that then obvious that that's possible?
In the sense that the statement is almost removing all possible obstructions that could have been
I see what
left over. Because this whole process of smoothing it out and mapping them is the process of removing every obstruction. So Grothendieck is basically saying if you remove all the obstructions, then you have a topological space.
Yes, that's a good point. Okay. Well, we're making progress. It's a good span of things. I'm sure there are fragments from what we've said here that are just the most bizarre connections between different fields.
There is one other point I want to make. It's slightly related to something that was previously said, where you mentioned about inducing convergence between geodesics as something to do with consciousness in mathematics space or whichever space. So typically when one wants to induce a convergence between geodesics, it is like saying that one is somehow spontaneously putting in there some mass energy. And if this has to happen spontaneously, the only way that could happen is if that space was somehow being compactified. So for example, I'm just taking this kind of motivation from Kaluza-Klein theories. You start with a higher dimensional space and you compactify some dimensions, then those compact dimensions become like gauge fields. So I'm thinking of them as mass energy. And if you decompactify, then some matter or energy can convert back into space degrees of freedom. So in that sense, what a conscious observer is really doing is compactifying some form of space such that this compactification results in mass energy, and this mass energy leads to convergence of geodesics. And in that sense, completion is like compactifying space-time, and or let's say space. So completion is like a compactification of space. And in a sense, when you compactify space, there's a limit up to which you can do it. because there is this bound that you cannot put too much space together. So that's the limit. But in that sense, another way to think of completion is in terms of compactification.
Right. I mean, look, in our models, there isn't a heck of a lot of difference between, curvature and dimension.
Yeah.
So that tends to, that difference, that normally, I mean, it's a good point that in the Kaluza-Klein, tradition, one is really doing a trade-off between curvature and dimension. I hadn't really made that connection before.
No, this is exactly what you mentioned with the other more practical example of what happens to a photon when you change dimension, right? So precisely we can take this the 5-dimensional Kaluza-Klein theory. In 5 dimensions, when you have only gravity and nothing else, and you compactify 1 dimension, then you get gravity, and that one circular dimension becomes the electromagnetic gauge field.
Sure.
So now you have a photon after compactifying, and when you decompactify, you can imagine like that photon degree of freedom got converted into space.
No, I understand. It's a good analogy for dimension change. Compactification is a good analogy, except that it isn't continuous. It's unlike, in our models, because we don't have fixed topology in our models. We don't have sort of the, oh my gosh, where did this compactification come from? I mean, like in Kaluza-Klein theory, it's like it always was that way. You don't have dynamic compactification, do you?
No.
I don't think any of those models have that, because they don't imagine the possibility that space-time could change its topology willy-nilly in that fashion.
Right.
But we do have that. But it's a good point that that's a way. So in the d-dimensional physics collection, that is, I mean, that's worth understanding, except I don't think it's going to be the right thing, because we want continuous dimension change. And that's always discrete dimension change so far.
Right.
Well, okay.
And also for the case of the observer, we want it not globally, but locally. Because what the observer in mathematics space or in physical space, what the observer is doing is something local where there is convergence of geodesics.
Right. I need to go because fairly soon I have to give a talk at some oh boy, there's a comment on a live stream about what are the open sets in this topology in this final topological space formed by morphisms. Wait a minute. If you can define open sets, you can talk about convergence in terms of sets. I'm not sure quite what that's referring to, but yes, do you understand, Xerxes or Jonathan? Can you comment on that? I'm not a big fan of open sets generally, but maybe I'll get converted by thinking about them in this context. Yes.
Well, I think the person is just making the comment that, in the ordinary axiomatization of analysis, that, the notion of smooth convergences of spaces and things
depends on open sets.
In terms of open sets. And
right. If you don't have them, you don't necessarily have that continuity, which is why, in our case, when you have singularities and so on and event horizons, that is a failure of the ability to have open sets, or even when you have these topological obstructions and particles and things.
Right.
Like, whoops, there's a particle there. You can't have a continuous limit because, oops, you hit a particle.
It's funny that you dislike open sets and yet we're using them in the trivalent graph case.
Well, that's why I didn't like the trivalent graphs. That's why I waited 20 years to do this project.
Right. I think it's quite elegant, considering edges without endpoints and things. Well,
I know, and as you know perfectly well, in the end, that stuff is all equivalent. And
right.
Well, I wouldn't complain too hard. Otherwise all this stuff would have been done before you were born. Right. Much more fun this way. Plus you've accelerated it by some huge factor. Yeah, it reminds me of the many things I think should have been discovered before I was born, but weren't. In any case, okay, I'm supposed to give a talk to some education conference in Cambodia in a little while. So I should, what's that?
Have fun.
Yes, hopefully I will. I think it'll be interesting. Talk about the importance of the computational view of the world to and understanding that. And I think, in a sense, we have the although it isn't really understood yet, we have kind of the ultimate creation myth for that idea. Namely, if the universe is computation all the way down, it really does make sense to understand things computationally. If it turned out that wasn't the case, if the universe was mathematical in the sense of continuum mathematics all the way down, it'd be a different story. And maybe there's a connection here at a very philosophical level to our discussions about. See, I do need to understand this. I think we need to understand this interpretation of consciousness.
Yes.
What's that?
Well, I was going to point out the rather amusing connection between we have discussed before between Penrose's non-computability of consciousness and the undecidability of the word problem.
Wait a minute. Explain.
So the statement that consciousness is cannot be made computable actually can be made a perfectly formalized and true statement in this view by stating that the general word problem is undecidable and that therefore it's not possible to construct a fully causal invariant representation of an arbitrary multi-way system. You can only construct causal invariant representations of localized patches of it.
So you're saying, therefore, the full consciousness, as in our black hole consciousness that kind of absorbs the whole universe, isn't possible.
Yes. So if you adopt okay, suppose you had a pure definition of consciousness that was some system in which their local representation was strongly normalizing and confluent, then if the universe is produced by a universal computational rule, which it obviously is, then such a consciousness, it's true that such a consciousness could not possibly exist.
Yes, I understand.
Such a consciousness would not be computable because of the unsolvability.
If there was a genuine consciousness in our definition of consciousness of being able to sort of absorb everything, that consciousness by definition, and it's the same statement as the fact that at 10 to the 400 degrees of freedom, you don't get to absorb them all in your brain.
Right. And so that there's a way in which you can actually formalize the Penrose argument.
Right, but that argument is all it's saying is there is no omnipotent, omniscient consciousness.
Right.
I mean, we're giving a proof that there can't be an omniscient consciousness, and if your only definition of consciousness is an omniscient one, then you're out of luck.
Right. Some interesting theological implications there.
Well, okay, so write a note down here just so we remember this point. The omniscient consciousness. Basically, the claim is
the claim is that the Aquinas conception of God cannot know the truth values of undecidable propositions, which is a somewhat amusing theological implication.
Well, yes, right. I mean, it's almost a proof. It's a proof of the non-existence of an omniscient God, right? I mean, because basically it's saying the only that's saying in our definition here, it's not possible to have. I mean, this is sort of obvious at some level.
It's not possible to have an omniscient God who is also recursively enumerable.
And or constructible in our universe.
Right. If we allow God to occupy higher levels of the arithmetic hierarchy, then you can.
Then all bets are off.
Right.
But then we also have a fundamental event horizon that prevents us from interacting. I think that we went through this before. There's I don't know what kind of event horizon to call it, between different levels of the arithmetic hierarchy.
Right. But yeah, I agree. There definitely is one.
Right, but so the point here, just to make a note so we don't forget this, the point here is the only way to have one, well, how to say this? Oh, I don't know. I think that's you know, by definition, not constructible in our universe. Can't exist in our universe because, I mean, this is obvious from as soon as the universe has computation universality, this is pretty obvious. Can't have this. Anyway, okay. Well, a pleasure, and to be continued. And thanks to folks on our live stream. Not so many comments today. Maybe we went off in way too complicated a direction, or maybe it's holiday time for everybody. Anyway, all right. I need to run. See you guys